Shall I start, ma'am?
Yes, Archana, you can start.
Okay, ma'am. A very good morning to one and all present here today. I am Archana Aruljyoti from the Department of Electronics and Communication Engineering, here to host today's workshop on SoC design methodology using Intel FPGAs associated with one of the world's largest CPU manufacturers, Intel. Now, I would like to extend my first and foremost gratitude to our Honorable Chairman, Dr. V. Babu Manoharan Sir, our Managing Director, Mrs. S. Jessipriya Ma'am, and our Executive Director, Mr. B. Sashishekar Sir, and our beloved Principal, Dr. P. Ravichandran Sir, for giving this opportunity to conduct the informative workshop for 3 days. It's my pleasure to welcome our Honorable Speaker, Mr. K. Padmanabhan, Program Specialist, FPGA, University Outreach. I would also like to welcome our department heads, Dr. C. Nyanakausalya Ma'am, Staff and Student Affairs, and Dr. J. Rohini Ma'am, Lab Affairs, for their ceaseless support. And finally, I would like to welcome all the participants present for this faculty development program. We welcome you, sir. It gives me immense pleasure to welcome Mr. Padmanabhan, the knowledgeable speaker of today's workshop. Thank you, sir, for joining us today. I would like to give citation about our speaker. Mr. Padmanabhan is the software enabling and optimization engineer in Customer Experience Group at Intel PSG. He has a postgraduate degree in Applied Electronics from Anna University, Chennai. He has more than 14 years of experience in digital design for both FPGA and ASIC. Before joining Intel, he worked as a chief faculty in School of VLSI Design and as an assistant professor and project coordinator in MSRAS Bangalore. Now, before moving on to the session, a few instructions to be followed by the participants present here today. I request all the participants to stay muted throughout the session. Kindly type your queries in the chat box, which will be answered by the speaker at the end of the session. The feedback link will be posted in the chat box at the end of the session, and all the participants are requested to fill it. Now, I request Mr. Padmanabhan sir to take over the session.
Yeah, thank you very much, Archana. Thank you for the warm introduction.
Thank you,
I'll share my screen. So, very good morning, everyone. Welcome to the third day of faculty development program on SoC design methodologies using Intel FPGAs. So I'll give you a quick background. For the past 2 days, we worked on the Intel FPGAs using the Quartus Prime design software. We did the Quartus Prime design software tool flow, and we performed timing analysis yesterday. And then we also have gone through the SoC FPGA design flow. We'll continue the same today with SoC FPGA design flow, lab demo and hands-on with in detail. And then we'll move on to the debugging techniques, how we are going to debug the design with a different set of on-chip debugging techniques, what is available from the Intel Quartus Prime design software. And a quick simple background again. For the first day, we were developing the RTL. And yesterday, we were using the intellectual properties. And then we developed the SoC design, IP core-based system on-chip design. And what is the basic objective in the other discussion here today is like we are going to use the concept called as high-level synthesis, in which we are going to use the tool called as Intel HLS compiler, which is called as a high-level synthesis compiler. So what we are going to do is we are going to convert the C or C++ code into an RTL. So after converting the C++ code into an RTL, we are going to analyze and see that what happens when the code gets converted into RTL and what are the different methods of optimizing it. There is a simple lab demo based on that. And then I'm also going to provide you the details on when do we need to go for RTL and when do we need to go for HLS. So RTL versus high-level synthesis and the basic concept of high-speed interfaces. And then how do we use Intel FPGAs for AI, artificial intelligence and machine learning. So these are the topics we are going to cover. So let me explain that one by one. And if you have any queries at any point of time, please let me know. And we can go ahead accordingly. Okay, a quick recap for around 10 minutes to just give a background what we discussed yesterday before we move on to the SoC FPGA lab. So we all knew that the SoC FPGA devices integrate both the processor and FPGA architectures into a single device. So when we were discussing yesterday, when we were going through the NIAS soft core processor, the soft core processor is going to use the resources which are present inside the FPGA. I have also mentioned that it is available in two variants. One is called as the economy variant and the other one is called as the fast variant. The economy variant is area optimized, whereas the fast variant is performance optimized. So why do we need to have both processor and FPGA on a single chip? The advantage is integrating the high-level management functionality of processors. We need to perform real-time operations, extreme data processing, or interface functions, right, into a single device, makes you to get a very powerful embedded computing platform. So we wanted to design an embedded system design using FPGAs, right? As I discussed with you earlier, we had only FPGA, then the processor has gone into the FPGA and the DSP capabilities are also present in the same chip. So when you have everything inside the same chip, you get higher integration, lower power, smaller board size, and higher bandwidth communication between the processor and FPGA. And they also include a rich set of peripherals, on-chip memory, and FPGA style logic array and high-speed transceivers. All are available in the SoC FPGA. Right, now let us move on to the next important logic. As you can recollect from the yesterday's discussion, we need to perform an embedded system design using the Cyclone 5 and ARM. So we need to design using the hardcore processors. You can see that the processors in SoC FPGAs can be hard or soft. What are hardcore processors? When we say the hardcore processors are implemented in the fixed silicon logic of the SoC FPGA, similar to the serial transceivers. So the idea is, when it is a soft core processor, it is going to use the resources inside the FPGA. Whereas when it is a hardcore processor, it is not going to use the resources inside the FPGA. Instead, it is a dedicated chip which is immersed inside the FPGA fabric. What is the greatest advantage here is hardcore processors, right? They offer higher CPU performance. They can operate up to 1.5 gigahertz. So that much operating frequency is not possible with the soft core processors. And it also depends on the factors such as processor architecture, clock rate, and process technology. Right. Now, can we call all FPGAs as SoC FPGAs when you say no? Right? Because the Max 10 device which we were discussing is having only the soft core processor. So what are SoC FPGAs when you say you have a hardcore processor that is immersed when you say? That means you have the Cyclone 5 FPGA, ARIA 5 SoC FPGA, Intel ARIA 10 SoC FPGA. So these SoC FPGAs have a dual core ARM Cortex A9 that is immersed inside the FPGA fabric, whereas the Stratix 10 and Agilex devices, right, the high-end devices use the quad core application processor A53 that is immersed inside the FPGA fabric. That's what I explained. And to get again a simple background about the soft core processors, we developed the soft core processor based embedded system design yesterday by using the NIAS 2 processor. What is the greatest advantage here when you say the NIAS 2 processors are implemented in the programmable logic? That means it is implemented on the FPGA side. Therefore, you can see that it uses the on-chip resources, such as it will show how many logic elements, how many multipliers, and how many memory are instantiated by this design. And you can also see the performance and the cost of a soft core processor mainly depend on the FPGA in which the processor is instantiated. But you can see that the performance and the cost are typically lower when compared to hardcore processors. So when you compare the hardcore processors, the performance wise, right, as well as the cost wise it is lesser because you don't need to invest for a dedicated hardcore processor. But you can also see the performance will also be lesser. And what is very important in this case, when you say sometimes we need to migrate from the soft core processor to the hardcore processor because you wanted higher performance, right? In some cases, when you work on an embedded system, at that point of time, it is easily possible for us to migrate from the soft core processor based embedded system design to hardcore. That means you can directly migrate your soft processor designs to hard processor implementations. That is also possible. Okay. Now let us move on to the next important principle. Now this has been explained to you in detail yesterday, but then let us get an overview, right? Why do we need to use FPGAs for embedded system design? So that's the question that needs to be answered. So you have the processor, and you also have all the peripherals that are attached to it, and then that means you have the specific hard processor system. And also you have FPGA in which there are peripherals on the FPGA side. By having peripherals on the FPGA side as well as on the processor side, what is the advantage if you say? You can increase the more number of I/O channels in your system. Because of that, you can add Ethernet, general purpose I/O, UART, everything whatever required for creating your embedded system. And another major important thing is co-processing. That means you can use the FPGA as a co-processor element, and you can use the processor and co-processor in order to ensure that for high speed or high compute intensive algorithms, you can process, right? Or you can use it for image vision algorithms or high speed digital signal processing applications. So in signal processing or image processing or packet processing applications where you have the compute intensive algorithms, right, from software running on a processor to hardware. That is one more important application where we can use that. Okay, today when we discussed about the Intel FPGAs for AI, we'll get more details about it. And custom embedded controller. So this is very important. Again, you can see that how many number of processors, peripherals, interfaces are there, and that you can include to create an embedded system design. And finally, multiprocessor. The greatest advantage of multiprocessor means what you have multiple CPUs that are there, and it will be easy for us to accelerate your software development, code reliability, and increase maintainability. All could be possible, right? And now you can, it is an addition. You can design a multiprocessor system as a custom system inside a single FPGA, or to augment an external CPU or a digital signal processor, because you don't need to connect an external CPU and you don't need to use a separate digital signal processor, because in a single FPGA itself, you have the DSP capabilities as well as you have the CPU capabilities. So what can be avoided? You can use the single FPGA chip, which can work with the processor, and it can also have the DSP capability. So we can ignore using a separate external CPU or a digital signal processor. That's the greatest advantage. Okay, right. Now, what are the system level benefits? This also was shown to you, but to give a quick recap, you can see that earlier FPGA was a separate chip and the CPU was a separate chip. And now what happens is it is like a system on a board is transferred to system on a chip. Everything is present in a single chip. When all are present in the single chip, what is the advantage if you say? We are getting increased system performance. First thing. Second, reduced power consumption. Because when all are integrated as an IP core based system on chip design, the amount of power consumed should always be lesser, right? So reduced power consumption. Third one, reduced board size. And the fourth one is reduced system cost. So you can see that you are getting higher system performance, reduced power consumption, reduced board size, and reduced system cost. Right now we can see can get the best of both worlds. That's what is shown. So you can see the ARM processor system, and then you can see there is an FPGA. So ARM plus FPGA is equal to SoC FPGA. That means you have a dual core ARM Cortex A9, and then you have the FPGA. When both are added, then we are going to call that as an SoC FPGA. So this is available in the 28 nanometer FPGA. That means you have dual core. Whereas when it is high-end devices, as I mentioned, you will have the quad core application processor A53. So in simple logic, how do you specify here? The Intel SoC FPGAs are going to provide you the best of both worlds. That means you can use that as a processor independently. You can also use that as an FPGA, and then you can also use the capabilities of kitting, the powerful compute or embedded computing platform, where you can get the advantages of both processor and FPGA. Right. You can see there is the SoC FPGA portfolio, where you could see there is a low-end SoC, Cyclone 5, right? And then you have mid-range, Arria 10, and then you have high-end SoCs, which is having the Stratix 10 and Agilent. What are the things that need to be noted down here? You can see that you wanted lowest power and you wanted to get highest performance. When you require highest performance, we need to move on to the Stratix 10 as well as the Agilex devices, because which works on 14 nanometer as well as the Intel 10 nanometer device. What is the greatest advantage here? You can see that along with the basic resources like logic elements, memory resources, as well as the DSP resources, we also have the processor capabilities here. So if you go through here, the Cyclone 5 SoC can operate up to 925 megahertz. That means it has a dual core ARM Cortex A9, which operates at 925 megahertz. So this much higher frequency you may not get when you are trying to use that with a soft core processor based embedded system design. Okay. Now you can see that it has 925 megahertz, and you can see 25 to 110, right? KLE logic elements. And you can see up to 224 multipliers. That means you can see processor, and you can see the memory, and you can see logic elements as well as multipliers. That is useful for DSP applications. So handling DSP applications with the same SoC is possible because it has 224 multipliers, which can take 18 cross 19. So 18 cross 19 cross 224. That much capability is there in Cyclone 5 itself. Now, when we move on to Arria 5, it can operate up to 1.05 gigahertz. The performance of the processor is 1.05 gigahertz. And you can see this has 533 megahertz GDR3. And you can see up to 462 KL. Now you can see that this is having 25 to 110 kilo logic elements, whereas it has 462 KL. And you can see that here it is only 224 multipliers, but here you can see 2136 multipliers, 18 cross 19. Now, when we move on to Arria 10, right, which is mid-range, you can easily compare. Along with the FPGA, we need to have the processor. Here you could see that it works at 1.5 gigahertz dual core ARM Cortex A9. And you can see 1200 megahertz DDR4. Here you can see 400 megahertz. And then when we move on to Arria 5, it is 530 megahertz. But when we move on to Arria 10 SoC, it is 1200 megahertz. And here it is only 110 KLE. Here it is 462 KLE. And then here it is 660 KLE. And then when we move on to the multipliers, here it is 2136 multipliers. And here 3356 multipliers. Okay. And when we move on to the Stratix 10, which is our high range and which is our 14 nanometer FPGA, it uses 64-bit, right? So this is very important for us to note down. You 32-bit and then you can see dual core ARM Cortex A9, whereas here it is 64-bit quad core application processor A53. And then what is the greatest advantage here? You can see this is 660 KLE, but you can see here 4000 KLE. How many logic elements are there? That means you can see the FPGA is also larger. Along with that, you can see the hard processor system. That means instead of a dual core, you also have a quad core. That means the processor side is also larger and the FPGA side is also larger. That means you have the higher density in both sides. And here you have maximum of 2056 multipliers, but here you can go up to 11,520 multipliers. And the same when you compare that with Agilex device, now you can see that the number of multipliers, here it is 17,056. You can see that multipliers are increased, right? And then you can see that, okay, there is a compromise between the number of logic elements between the different set of devices, because it has to use a transceiver which can go up to 116 gig. Since the transceiver is going to sit right? The place that is occupied will be more. Therefore, the number of logic elements will be less. Here you can see that it is only 58 gig transceiver, whereas here you can go up to 116 gig. So 6 gig, 10 gig, 17, 58, and 116. From this, you can easily understand that when we migrate from one SoC FPGA device to another SoC FPGA device, definitely you are going to get higher performance. And it is going to best suited for the kind of applications what we want. That's what has been shown. Let us move on to the details here. What are the key features? What is the key takeaway from the SoC design methodology session when you say, we need to know in each and every FPGA, that is SoC FPGA, what is available on the processor side and what is available on the FPGA side. So it is easy for us to design an embedded system based on that. If you see here, Cyclone 5, ARIA 5 and ARIA 10, as I mentioned, has a dual core ARM Cortex A9, and whereas the Stratix 10 uses a quad core application processor A53. And now what is very important for us is the performance. If you compare the performance here, Cyclone 5 can operate up to 925 megahertz, whereas ARIA you can see 1.5 gigahertz, which is maximum. And similarly, you can see the logic density, as I mentioned in the previous slide, you can go up to 5.5 million logic elements. Where is KLE and where is 5.5 million logic elements, you can easily compare. Right, and I have stopped with only Stratix 10. I didn't move on to HLX. Now you can see that the transceiver's speed will be up to 6 Gbps and ARIA 5 up to 10 Gbps and ARIA 10 up to 17 Gbps and then Stratix 10 up to 28 Gbps. So now this is the SoC FPGA logic. We have Cyclone 5, we have ARIA 5, we have ARIA 10, and then we have the Stratix. Right. Now, how it look like when you say, if you could see, this is the hard processor system, right? And then this is the FPGA section, the HPS section and the FPGA section. You have a dual core ARM Cortex A9, and then you also have the memory RAM, and then you have GPIO, you have Ethernet, you have USB, SPI, CAN, right? And then you have timers, DMA, UART, all are available on the HPS. And on the FPGA side, if you see, as I mentioned on the first day, you can see you have an 8-input adaptive logic module. That is your factorable, right, lookup table. And you have variable precision DSP that is available, which is a multiplier. You have M10K memory. One small logic is, if it is a Max 10 device, you have M9K. Whereas when it is a Cyclone 5 device, each memory block will be 10K. That's the only difference, okay, M10K. And the maximum up to 640-bit MLABs. So one memory logic array can go up to 640 MLABs. That's what is given here. Right, and along with that, you also have the PLLs, the clocking resources. All these things are available on the FPGA side. Now the question is, we have the FPGA chip as well as the HPS chip, the processor, both are present in the same chip. How are we going to communicate when you say we have a bus interface here? HPS to FPGA, which is called as hard processor system to FPGA, and then FPGA to HPS, that is available here. And how do we do this? With the help of the different set of chip interfaces. HPS to FPGA, FPGA to HPS, and FPGA to SDRAM interface. All are available. Okay, these are the things that need to be taken away. Right. Next important thing which we need to highlight is on the high range or high-end SoC FPGAs. So in this case, we need to discuss about the Stratix 10. As I mentioned earlier, you can see there is a quad-core application processor A53, and then you have a Neon, which is a floating point unit, and you have the other interfaces like UART, SPI, GPIO, etc. And you can make communicate between the HPS and the FPGA. Right. As a summary, what you can see on the processor side, you will have quad-core application processor A53, which is based on the 64-bit ARM version 8 architecture. And on the FPGA side, if you see, it is going to have the 8-input adaptive logic module, 8-input actionable lookup table, and it has a variable precision DSP block. Will be available on the FPGA side. Right? What is the proportion logic? Right? If you see, the hard processor system can take a large, a smaller portion of the device. So this I will show you while showing the demo. When you check the hard processor system in the Cyclone 5 device, you can see that most of the FPGA section, right, is occupied by the hard processor system. Because if this is the FPGA chip, right, and this is the place allocated for the hard processor system, it is fixed now. So you can see that in a Cyclone 5 device, this much space is occupied by the processor. Whereas when you compare the same with the Stratix 10 SoC FPGA device, this much is the area of the FPGA. And what is the area taken by the processor when you say this is the 1T? Right? That means you can see that easily you can compare how much is the bandwidth, right? And how much is the density that you can easily think about. Okay, let us come to the quick summary now and easily start comparing them. Okay, what is very important for us to note down is sometimes you work on the mid-range SoC FPGAs and you wanted to migrate your project to high-end SoC FPGA. So where we have to be very, very careful when you say, when we work on the mid-range FPGAs, it is a dual 32-bit ARM Cortex-A9. Whereas when you are migrating that to Stratix 10 SoC, it is 64-bit. That we should keep that in mind. And FPGA to HPS bridge can be operated on 32, 64, or 128. Whereas in Stratix 10, it is only 128. So these two important points need to be taken care of. Right. And what are the other important comparisons which we should have, right? So the processor cores are only 2. And then here processor cores are 4, but everything here it is 32-bit register size. Here it is 64-bit. When you migrate, we have to be very, very careful with that. So this is a summary. Now, what is very important at this junction is if I wanted to use only the FPGA section, and I am not going to touch anything on the processor side, will that be okay when you say yes? We can definitely do that. So on the FPGA side, it looks like an FPGA, works like an FPGA, standard FPGA development flow, and the standard FPGA development tool, the same software we are going to use. Intel Quartus Prime Design Software, Platform Designer, and I will explain about System Console today. All we are going to use on the FPGA side. And on the processor side, I'm going to use only the HPS when you say. It will exactly look like the ARM processor system. It works like an ARM processor system. Typical ARM processor development flow and typical ARM processor development tools. And it is going to show you the cross compilers, debuggers, JTAG tools, program trace, everything, etc. will be exactly looking like on the ARM compiler side. Right. Now let us move on to the lab demo. That means I'm going to show you a demonstration of developing an SoC FPGA design in which we will have the processor as well as the FPGA, both will be present, and how are we going to build the embedded system, and we can understand how the peripherals are connected, and we can analyze the system, right? And then we can perform analysis and elaboration, and we can compile the design. Right, so let me enter into the details now. This is the lab exercise using the Intel FPGA Quartus Prime Design software with an SoC. So before we enter into the lab, how do we start this lab? Where are the informations that are available? When you say, there are two places where you can get information about these labs. One is called as the rocketboards.org, and the other one is the Terasic. Okay, I will explain both to you right now. If you go to the Terasic website, So in the thoracic website, if you say about thoracic, right, and then you can directly go to products. In the products, you can click the SoC platform. Okay. In the SoC platform, what we are going to cover today is two kinds of SoC FPGAs. Both are based on the Cyclone 5. One is the DE1 SoC. The other one is the DE10 Nano. Right? Both are available here. Let us try to solve this problem now. First one, the DE1 SoC board. Right? Just click the DE1 SoC board. Open that. And in the D1 SoC board, okay, what you need to see on the left-hand side is the overview, specifications, layout, and then resources. Okay, now if you see what is available in the D1 SoC board, let us understand that now. If you go through this D1 SoC board, let us just click through the specifications here. So this is an SoC which has the FPGA section, Cyclone 5, and it also has the HPS, which is the dual core ARM Cortex-A9. Both are available here. Okay. Now you can see that it has both the processor as well as FPGA. Both are available here. Now what we need to download is the resources folder, right? Just go to resources. In the resources, you need to download two things. One is the D1 SoC user manual. Okay, and then the D1 SoC CD-ROM. Both need to be downloaded. Okay, the moment you click here D1 SoC user manual on the right hand side. Okay, when you click that, the moment it gets downloaded, I will show you what is present inside that manual and what are the informations that we should look into it. Okay, so let us just open that board. So this is the D1 SoC user manual. What is available here when you say, you can use this board as only FPGA. The examples only for the FPGA section. And examples only for the SoC section. That means it is going to show you how we can use only the HPS section of this board. And examples of both using HPS and FPGA. So that's a spelling mistake here. Okay. So we should use HPS as well as FPGA. Both, how do we use? We have to use both HPS and FPGA. And we need to use only HPS, that is only on the software side, right? On the only the processor side. And then you are going to use only the FPGA side. In this lab manual, there are examples which explains you that how are we going to use this SoC board for only FPGA operations and only the HPS operations and both SoC and FPGA. So on the FPGA side, if you see, you have all the peripherals that are available here, and then you can see that you have push button, slide switches, user LEDs, 7-segment displays, etc. These were the things we used on the first day with the Labs LAN setup. And when you go through the hard processor system, right, you have an 800 megahertz dual core ARM Cortex processor is there, and then you have a micro SD card, and then you have a 1 gigabit Ethernet, accelerometer. All these things are available on the HPS side. So if you see the board, it looks like this, in which the right-hand side is the HPS side, which is the processor side. On the processor side, you can see micro SD card, Ethernet, DDR3, SDRAM, UART to USB, accelerometer, right? And you have HPS user LED, HPS reset. All these things are available on the HPS side. They are fixed on the HPS side. Similarly, you can see the peripherals which are available on the FPGA side. Now you can see push button, switches, 1-segment display, LEDs, etc. They are available on the FPGA side. Now, what is important for us is how are we going to communicate between the FPGA to HPS as well as HPS. It is possible to use only the FPGA section. It is also possible to use only the HPS section, but it is also possible to use both FPGA and HPS. So this is what is available in this specific lab manual. You can just go through this and get more details about what are the different set of examples that are there. Okay. Right. One more important thing. When we enter into this website, right, what is important for us to note down is the CD-ROM. We have to download this. What this CD-ROM has, when you say this CD-ROM has all the examples, right, whichever has been mentioned in the lab manual. That means you don't need to create any lab files. They are already available, so it is easy for us to take it and then understand what is happening, and then we can reuse that code, or you can use it for your custom application. Right, but only thing is, the moment you click this D1 SoC CD-ROM, it will directly take you to the page where you need to become a member of the Terasic. If you already have the login, that is username and password, you can provide that and then you can download it. If not, you can just click this page, which will take you to provide details. You can provide your details, email, password, the company name, you can give your institution name, and you can provide all the address. You can see here academic user information. You can provide here university, college, department, position, and department webpage and submit. Automatically, it will provide you access of all these materials, which you don't need to spend any time. You have all the materials ready. Okay, assuming that you have downloaded that CD-ROM, okay, what will be inside that? I will explain. Before that, I will also show you in another website where you will get more information. So we have discussed about the Terasic website now. Okay. Now let me explain you with another important scenario. Okay. So go to rocketboards.org. Okay. All right. So just let us go ahead with the page and then try. So go to rocketboards.org. Here you can see the documentation. You can click here. And here you can see the training and tutorials. The only thing is you have to select corresponding device. What is important here is a cyclone file. This is what we are discussing today. I request you to go through this now. Ultra cyclone 5 SoC board, right? Or we can say D10 nano board, right? D10 nano or D1 SoC. So anything you can take it here. The moment you provide the details, right, you will get more details about all these boards, where you have the GHRD, which is called as the Golden Hardware Reference Design, where you don't need to create anything from scratch. Everything will be available, right? This will help you to get more logic. Sometimes you wanted to get more projects, right? What are the projects that are available in that specific board? That also you can get it. On the right-hand side, you can select which board you want. And based on that board, you can see there are multiple examples, right? So for example, if you pick this specific project, this will take you to the page where you will get more information about the specific example. Triple speed Ethernet design example. What is the introduction and what is the release content and what is the quick start guide? All the details are provided. The complete architecture overview and how do we connect it, everything is explained in detail, step by step. So it is easy for us to get more information about it. Okay, now let us move on to the lab. After you download the Golden Hardware Reference Design, either from the Terasic website or from the rocketboards.org, you can see that this is the Golden System Reference Design Manual. After downloading that, what you are supposed to do, when you say this is the typical design flow which we are going to follow. In this flow, what we are going to do is, we are going to take the Quartus Prime design software. That means create or open. So we can create from scratch or we can open what is already available. In our case, we are going to open what is already available. So open the Intel Quartus Prime design software project. And from there, we will directly move on to the platform designer. So in the platform designer, we are going to create our open platform designer project. We add or configure the hard processor system IP. Then we connect the components, we generate the system. And from there, from the platform designer, we will again come back to the Quartus Prime design software. We instantiate the platform designer in the Quartus. Then you run analysis and elaboration, compile the project. What we won't do here is we are not going to implement the design onto the board. Therefore, our lab exercise will stop at compiling the project. Only the last step we are not going to. Right? Since you don't have the board availability, we don't need to try that. But we can compile and then understand what is happening in each and every case. So this is the typical design flow, which I am going to show you right now. So you can see that we open the Intel Quartus Prime design software project, which already has selected for the SoC FPGA. From there, you move on to the platform designer and you configure and then you connect all the components, generate the system. And from there, you instantiate the platform designer project, run analysis and elaboration, and then you compile the project. Right. So let us try that right now. Okay. So let me open that example and then we'll go ahead with that. Okay. So let us first open the lab. Using Intel SoC FPGAs is the lab which we are going to do now. And you don't require the board for this, as I mentioned. And we are going to stop after creating the embedded hardware design project. Okay. The first thing what is important for us is to download the system CD. That's what is explained in the lab. So what is the objective of this lab? We are going to understand the system on chip workflow for implementing the FPGA designs alongside hard processor system. Along with the hard processor system, we are going to see how do we use the FPGA and HPS in an SoC workflow. That's the basic idea of this lab. And the system is developed with the platform designer. And then we are going to integrate that into the Quartus Prime design software. And then we are going to compile it. Okay, what we have downloaded, that means we are going to use the Golden Hardware Reference Design, GHRD, which is available with D1 SoC Intel FPGA Development Kit. So when you go to Terasic website and when you download the D1 SoC CD-ROM, there you will be getting this specific logic, right? What would be inside this? I will show that to you right now. The moment you enter into this specific CD-ROM, this is what I have downloaded and kept here. The D1 SoC CD-ROM, if you open, right, once you get this, right, which is unzipped, you can see there is a folder called demonstration. Okay, you can see multiple folders like schematic, tools, user manual, data sheet, etc. We will go one by one. Okay, let us start with the demonstrations first. When you open the demonstrations here you can have three subfolders mainly. One is called as FPGA, which shows that the examples, whatever is inside, is going to use only the FPGA section of the D1 SoC board. So if you click that, you can see all the examples. The SDRAM RTL test, SDRAM NIAS test, PS2 demo, IR, right, Golden Top, audio, ADC, right, all these examples are going to use only the FPGA section of the D1 SoC board. Then if you click the SoC folder, the SoC folder has some 4 projects, which is going to use only the HPS section. That means the hard processor system section of the Cyclone 5 FPGA. So if you open any one of these examples here, you can see it has only the C code, right? So using only the C code, that means you are going to use only the processor section. That's what is the idea. But if you open SoC FPGA, that means it will have folders which is going to use both the FPGA as well as the HPS section, both processor as well as FPGA we are going to use. So if you just open any one of the example here, you can see FPGA RTL. you have the entire Verilog code and then the system, and you also have the C code for it. This is the way how the D1 SoC CD-ROM has been built. So now what we are going to do in this lab is, we are going to take the my first HPS FPGA as the project, and we are going through the entire compilation process. So starting from platform designer, taking that to the Intel Quartus Prime design software, perform analysis and elaboration, and then we will stop till compilation. So how do we go ahead with this? Just to copy this folder. So inside this, right, demonstrations folder, you will have SoC FPGA. Inside that, my first HPS FPGA. Okay. Before going into the lab, what are the other important information? Since we are very new to this, you can click this user manual. This user manual folder will have multiple manuals which will help you to understand in detail. For example, I wanted to use only the FPGA section. You can go through this, my first FPGA PDF. You wanted to use only the processor section, my first HPS, only the processor section, how to use. I want to use both, my first HPS FPGA section. This is what I'm going to show you. But still, you wanted to get more details? Yes, you can. For example, if I open this, my first HPS, it is going to use only the C code, what is mentioned. So my first HPS. So you can see that the document is going to explain only the software development flow. It is not going to provide you any detail about the hardware development flow. Directly take the software development flow, take the C code, create a make file. You are going to boot Linux, and then to the SD card, you are going to see the output. All the informations are provided. How to create the make file, how to compile it, all these information are. Okay, right. So this is possible for you to do by going through this. But how do we start this SoC? When you say, click this learning roadmap. This learning roadmap will give you a clear idea how to start with this. There are 6 guides. First, you should start with the quick start guide, then getting start guide, then my first FPGA, then my first HPS. So after learning something about FPGA and HPS, then you can combine them together, my first HPS and FPGA, and then go to control panel. This is the way how you can start going through and getting an idea. Okay, let us go through the lab now. Come back. Go to the demonstrations folder. Go to SoC FPGA. Take the first example, my first HPS FPGA. Copy that. Then we'll go to C drive, create a folder, and say SoC project. Okay. Inside this SoC project, test this. My first HPS FPGA. Okay. Now come back, minimize this, open the Quartus Prime design software. So click here, open project, and go to C drive. SoC project 1. Inside that, my first HPS FPGA. Inside that, select SoC system.qpf, which is the Quartus project file. Select that and save open. We should have the Quartus project file to open the Quartus file. This is very important step. What it is showing is the design has been generated. The golden hardware reference design has been generated in the 13.1 version of the Quartus Prime design software. But now what we are using is 18.0 or 18.1, right? So because of that, we need to upgrade all the IPs, right? In order to get into the details. So what you should do in this case is IP upgrade recommended is there. And then it shows that the launch IP upgrade tool. So we should upgrade the IP before we get into the details. So you can also get into the lab manuals by going through these details, but At this junction, it is very critical and important that you should upgrade the tool. Okay. So whenever you get a red yellow banner, just click here. Launch IP upgrade tool. Okay. And what we need to select here is perform automatic upgrade. This automatic upgrade will take 2 to 3 minutes, so that it will upgrade all the IPs in our design, and which should be taken to the corresponding right. So what is the corresponding version which we are using? To that it will be taken care. You can see down on the information side that it is upgrading all the IPs one by one.
Sir,
Yeah, so you can see that it is showing 100%. What is the meaning? You have done the regeneration status is success. That is SoC system is done, and in system sources and probes, everything is success now. Now what we should do, we should close this so that the design is ready. Let us go on to the next step. Now, what is the first step which we need to go through? It's like after upgrading the IP, open the GHRD tab. You can see it is done for the Cyclone 5 device. Open that. And now what is very important for us to note down is the hexadecimal displays. You can see it uses 6 hexadecimal displays, X0, X1, X2, X3, X4, X5. Then you can see the HPS side, which are all called as the hard processor system side, which is HPS. And then you can see the FPGA side. All are available here in the GHRD file. This is the top file. Okay, what is very important for us at this junction is we need to go through this design and understand what is present inside the SoC. So first let us open the platform designer file. Okay. So go to tools, and then from there go to platform designer. Okay. After opening the quarters, go to tools and then go to platform designer. So when you open the platform designer, since the design is already created, right, you will be having the QSys file ready. Just select SoC system.qsys and say open. Okay. Now open this SoC system.qsys. When we open this SoC system.qsys, you can see this is the HPS, which is the hard processor system. Here you can see what are the important interfaces which you should understand, right? What are the specific connections, right? You can see H2F. That means this is processor to FPGA, HPS to FPGA AXI clock, HPS to FPGA AXI master. Right. Similarly, I am able to hear some background noise. So if you are not having any questions, can you please mute?
इसको भी कर रहे हो क्या? कर देंगे सर, हटा लो इधर। हटा के रख दे, इसमें क्या है? आप तो सारा साफ सुथरा कर रखा है, तो ऐसे बिखरा तो पड़ा ही नहीं है, अभी जैसे पहले बिखरा पड़ा रहता है। अब तो साफ सुथरा ही है, इससे ज्यादा साफ तो सर चाहिए क्या?
Yes, sir. Can you please mute if you are not having any questions?
वो एक का पैसे एक्स्ट्रा लगता है। मेटल तेरे लिए दिया होगा, 2 बार चाय लेके नहीं, थोड़ी सी भी नहीं देता। कल 2 बार लेके 3 चाय तेरे को दे दी होगी। सुन देख मैं ना पता कल राजस्थानी है नहीं सर, मैंने एक्स्ट्रा चाय 2 बार आई थी सर ने, 2 बार मंगाई, कल 3 चाय चाय वही है बादू दे देता, अब ये नहीं देते। तो देख ले क्या तुम्हें पता, राजस्थानी नहीं देगा ले क्या मैं बताऊं तुम्हें, तो सिर्फ चिल्ला चपाटा खड़े हो कोई हो ना हो ना, चिल्ला चपाटी तो वो कब देता, वो तो पैसे लेता।
Can anyone help me out? I am not able to do anything.
Sir, Niraj Gupta sir, can you mute your audio, sir?
Yes, sorry. Sorry, madam.
Okay, sir, you can continue.
Yeah, thank you. Now you can see the hard processor system where there are 4 important things which we need to understand. One is the HPS to FPGA, which is the hard processor system to FPGA, right? That is a processor to FPGA AXI clock. Then processor to FPGA AXI master. So AXI clock, AXI master. Another important thing is we also need to see that on the FPGA side. You can see that FPGA to HPS. It shows here F2H. So F2H AXI slave and H2F lightweight AXI clock. Okay, where are these informations? That's what we are going to understand right now. So when you double click this HPS, right, it will show the entire details that are available in the hard processor system. Here you can see that the ARIA5 or Cyclone 5 hard processor system uses the FPGA interfaces. Then you can see peripheral pins, HPS clocks, as well as SDRAM. Now you can see that when it is general, you can see what are the generic interfaces that are available. And here you can see AXI bridges, which is FPGA to HPS interface width, HPS to FPGA interface width, and lightweight HPS to FPGA interface width. So it shows that 64-bit, and then 32-bit. Okay. And now if you go down, you can also see that what are the other FPGA to HPS SDRAM interface module that could be added. You can use plus and minus button so that you can add all the interfaces which are required. And now when you click the peripheral pins tab, This is very important for us to note down. This peripheral pin stabs will tell you which are the interfaces that are the peripherals that are enabled, they are used, and which are the peripherals which are unused, that you can see from this tab. So if you look here very closely, you can see that Ethernet media access controller, Ethernet MAC, it shows unused. And the NAND flash controller, it shows it is unused. But you can see quad SPI flash controller, it is showing where it is set. The information is provided. Similarly, when you say SDMMC controller, where it is set, so the pin number is provided here. From this, you can understand that which are the peripherals that are enabled, they are used in our design, and which are the peripherals that are unused. You wanted to customize it and then you wanted to modify it, we can definitely do that in the system. And the third important thing is called as the HPS clock. The clock which is required for the processor, which is the HPS clock. So the HPS clock frequency, you can see the oscillator, the external oscillator frequency. You can see it shows 25 megahertz. And then FPGA to HPS, PLL reference clock. All these information are provided. And for each and every peripheral, for Ethernet MAC and for QSPI and for I2C, what is the clock that is provided? That information is provided in detail here. So this is very important for us to note down. And the fourth important option is the SDRAM. Whether you wanted that protocol to work as a DDR3 or DDR2 or LPDDR2, all these configurations will be shown here. So this you can see that DDR3, then DDR2 or LPDDR, the low power, whichever you wanted. So all these informations are shown here. Not only that, you can see the memory parameters because these are useful for high-speed interfaces where you need to connect them. So it is very critical and important for us to understand that. So go to the memory parameters and then you can see whatever frequency we wanted, we can select. And then the memory timing information and then the board setting. All these informations are provided here. Okay, so that is explained in the system content. Now we can come back to the main window where you have discussed the details of the HPS. Now, this is the processor side, and you can see that there are some interfaces. That means these are some peripherals which are available on the FPGA side. For example, you can easily recollect like what and all we connected in the yesterday's SoC. One is on-chip memory. The other one is the JTAG UART. You can easily understand what are the three important pins that will be there in the on-chip memory. One is clock, other one is reset. And for JTAG UART, you will have clock, reset, and then the JTAG slave, and then interrupt request, IRQ. Now, how they are connected, you see, there is a fundamental difference. When we create a NIOS-based embedded system design, you are going to use the Avalon memory mapped master and Avalon memory mapped slave, where we connected to the instruction master and then the data master. But here, since the processor is a dual-core ARM Cortex A9, what is the interface that is used is the AXI, which is the advanced extensible interface. Now we need to connect that advanced extensible interface AXI with our FPGA Avalon interface. Now how that is connected, you can see that. See the Avalon memory mapped slave S1, right? So that is what is to be connected to the master, which is the master. If you see here, you can see that is connected to the master, which is AXI master, that is correct. Similarly, you can see that the connection of the JTAG UART, so Avalon JTAG slave, that is connected to the JTAG slave, which is like F2H axis slave. The axis master and axis slave, they are connected. So all these informations would be known to us. So here you can see which is an axis master, which is HPS to FPGA axis master. And then here you can see lightweight, which is HPS to FPGA. So all these informations are shown, right? You wanted to add a peripheral, right? You wanted to add a new component. You can just click that in the IP catalog and we can add that new component to this design. Okay. But what is my suggestion is, since we are going to run the GHRD first go through the logic with the existing design. Just go through the steps which is available with the existing design. Generate the HDL and then generate the QSys file, integrate that in the Quartus Prime design software, compile and understand what is happening. Then later what you can do, you can take that design and you can customize it and use it for any kind of application. Right, now what we can do is, after we explore this, click here, generate HDL. And then you can click generate. Once it is generated, we can integrate that in the Quartus Prime design software. First, we will do analysis. Then we can perform compilation. So what are the steps followed? I will show that one by one to you. Okay, now we can say close. Okay, now either you can exit the platform designer, or else you can just click, right? You can exit from this place, finish, and then you can exit it, or you can minimize it, whichever you want. Now we can come back to the Quartus main window, right? And then first thing what we need to do is we should perform analysis and elaboration, right? First we'll do that. We expand this analysis and synthesis and do the first step, which is analysis and elaboration. So while performing analysis and elaboration, what happens is it takes the design and it is performing initial synthesis and shows you what is the RTL schematic, which is the technology independent schematic. Then we can perform the full compilation where we do synthesis as well as fitter operation and see whether you are able to see the resources, what is present on the HPS side and the resources which are present on the FPGAs. So all those informations we can get into the details. I will show that one by one to you. Okay, now what we should do is go to the tools and go to the netlist viewers and then go to the RTL viewer. Right, now you can maximize this and see the HPS, right, which is your SoC. If you click this, right, if you click this SoC system, you can see this is the SoC system. And here you can see the FPGA section. Right, and then you can see that this uses the clock, which is 50 megahertz. And then you can see all the FPGA resources which are used. Okay. Right, now what we can do is we can see that the logic utilization, total number of registers, pins, block memory bits, nothing is shown here because we have done only the RTL schematic. Now we need to do full compilation. So I'll click full compilation. It will take some time to compile the entire design. Meanwhile, we can go through the lab manual and understand what are the steps we have done so far. Okay, let it continue. Now, once we enter into this, the embedded systems lab, whichever I shown to you right now, and then you can see that whatever demonstrations we have seen, right? I mentioned that there are different set of examples, but we have seen only one, my first HPS FPGA. You also have my first HPS FPGA base, another project, HPS LEDX, another project, and D1 SoC GHRD, another project. All these projects are available. One by one, you can try and follow what is the step given in the user manual, right? Now, when you open this lab manual, Where we stopped is like we need to open the CD. This is what I given, system CD. When you click this link, automatically it will take you to the system CD. And what is the specific detail about this project is you don't require the board, as I mentioned. You directly download the CD-ROM manual. You can download the system cd.zip and you can enter into the my first HPS FPGA RTL. This is the place you can recollect. I went into the demonstrations folder, SoC FPGA, my first HPS FPGA and FPGA RTL. So this is the place which we entered. And the moment you enter it, I also showed you, you will get an yellow banner recommending that you need to upgrade the project. So we upgraded the IPs. And after upgrading the IP for 3 minutes, you saw that, okay, you have to click perform automatic upgrade. Then everything is done, so we can close. This is what is shown. You can recollect this. So perform automatic upgrade. Once it is done, we can click the close button. Okay, then what is the next step is you have to open the platform designer. This is what we did. When we opened the platform designer, there was a SoC system.qsys file, which was already there. You would have seen that I clicked that qsys file, which opened the embedded system project like this. When it opened the embedded system project, you can see that F2H, this is FPGA to HPS, and then you can see HPS to FPGA, both are available, right? Okay, so all the clock and reset inputs which are available, those informations we can take it. Now, the second important thing what we have done in this lab is examining the platform designer system. We need to get into the platform designer system and we need to go through that each and every step, what is happening. That's what we have seen now. The first thing is we double click this HPS scan and we have gone through the general interfaces that are available. And we have also seen what are the peripherals, HPS clock, SDRAM, etc. What is very important to note down in this case is when we click the peripheral pins tab, I showed you that which are the pins that are enabled. You can see that the following peripherals should be enabled. You should see that Ethernet MAC, Quad SPI flash controller, SPIM1, SPI controllers, UART, I2C and I2C1. All these controllers are enabled. That's what we have seen. I have shown you that where it is showing that it is set, where it is showing that it is unused, both informations I showed you now. This is what is shown. And what is very important for us is we have to ensure that the AXI interface is used in the system. Because in the earlier design, when we did that with yesterday's logic, there is no meaning of AXI because we used only the resources which are present inside the FPGA, and then the processor is also a soft core processor. But today, when we are using that with the HPS, right, since it is ARM-based processor, what is the kind of interface we are going to use today is the AXI interface that is used in the system. What is very important is you wanted to implement this, right? You can uncheck and then you can navigate the system and then you can get rid of it, whatever you want. That could also be done. Run this peripheral bugs table and you can generate the platform designer system, generate the HDL. And after generating the HDL, we are going to see how it works on the elaboration. That's what is shown to you. When we click analysis and elaboration, it showed this schematic you can recollect where we opened this SoC system and seen that this is on the FPGA side and this is on the HPS side. All the HPS information are shown here. Right, and then we need to compile the design. This is what I have done now. We can see that this is the longest processing time of the lab because it is going to compile, means it is going to perform analysis and elaboration. It has to perform synthesis and then it has to perform filter, all the operations. And now at the end of this operation, what are the two things we are going to compare is, first we are going to see in the flow summary, what are the resources it has taken, that is one. Second thing is what resources are used by the FPGA and what resources are used by the HPS. Both we can see that, which is the HPS resource utilization tab. And we are going to see the FPGA resource utilization tab. And then we can conclude this lab. So let us open the quarters and we'll see in which place we are available right now. So it is in 5-6 minutes, right? You can see that. Here it shows that how many number of registers it shows. 3134, right? And you can see total number of bits, block memory bits. You can see that. From this, you can understand that the design is not a small design, right? It takes a lot of time. So you can see that the logic utilization in ALM, it is showing not applicable till now because it has not placed and routed. So once it completes the placement and routing, it will show you how much it could be possible. Right? Let us wait for a minute. Meanwhile, I will also show you what is important in the slide also. So note down. Okay, we have stopped here. I will continue some 3-4 slides here. So how do we know that this is an SoC device? This is what I explained to you yesterday. Everything should start with yes. Okay. And you need to check whether when you drag that while performing the family device board settings, you should see that it should show the HPS scores. This I shown you while creating the project yesterday. Okay, so this is the greatest advantage of Platform Designer because it generates GUI-based system. It simplifies the complex system development, and it automatically generates the interconnect among various off-shelf and custom IPs. Everything you can see that it does automatically. And this is shown, and this is shown to you. And FPGA signals are shown. Yeah, this is one thing which you need to note down. When you open the hard processor system, you can see the signals which is on the left-hand side, where you can see the signals which shown, which is on the FPGA to processor side, that is as well as the processor to FPGA side, both will be there. And you can enable the general purpose signals if you want, all the GP signals. Okay, so this is done. And clock and what are the interfaces that is shown. Okay, this is shown to you. You can recollect this yesterday. When we gave Cyclone 5, it showed ARIA 5 or Cyclone 5 hard processor system. But you can see ARIA 10 hard processor system and Stratix 10 hard processor system, they are inactive. That means in this device, you have only the Cyclone 5 device. Okay, either you can connect the component directly, click the open dot and make a connection, or you can right click any signal and then from there you can, whichever signal you want, you can connect also. But this is the easiest method. Whichever signal you want, you click the open dot so that it will automatically make connections. Right, so this is what is shown. And we generated the HDL and we need to complete the design before we go to the next step. Right, we are in this place. Let us go to the quarters now. Hope within a minute it should complete. Now you can see that it shows 2210 logic elements, that is ALM. And how many number of registers, if you see, it shows 3289, right? And total number of pins, right? And then you can see the total number of block memory bits. Everything you can see here, how much it has used. Okay, now you can see that how many logic elements are there, ALM, how many registers are there, and how many number of block memory bits are there. All these informations are shown. Once it is 100%, let us open and see from the fitter operation. Now expand the fitter and go to the resource section. And here we can expand and see the resource usage summary. So in the resource usage summary, you can see that what are the ALMs that are used. So can you please mute if you are not speaking? If you have no questions, please mute. Yeah, thank you very much. So ALMs, you can see that what are the adaptive logic modules that are used. And you can see the total number of logic array blocks, how many it is used. So you can see the FPGA section in detail here. What are the logic array blocks that are used? And you can also see here hard processor system peripheral utilization. So till this place, it is showing that what resources are used on the FPGA section. And here it shows what is the resource that is used on the processor side. So all these informations are shown. How many memory blocks and what are the total block memory bits, everything is shown here. All these informations are shown to you. Right, so this is the basic logic. Now, what is another important thing is we have gone through what is the resource that is there, but we can also see the state machine weaver, right? We can see the filter operation as well as the state machine weaver, right? First, let us try that now. Go to the netlist weavers, and then we should go to technology map weaver post fitting. Now you can see that this is the FPGA section as well as the HPS reset. You can see that all the signals are available here. Right, the entire operation is available. Now, what happens on the FSM side? That also we can see. Go to the tools, go to the netlist weavers, and then go to the state machine weaver. This is the state machine that is present inside. You can see the source state, destination state, as well as the encoding. All these information are shown. It shows that at what kind of condition you transit from one state to another state. All these information are shown. Okay, exactly like a Quartus project, whatever we have seen yesterday, everything can be done with respect to the SoCs. Okay, right. What happens to the timing? Let us go through that. So tools, timing analyzer, you can. And say create timing netlist. Okay. Now you can see, are there any clocks in the design? So you can see what are the clocks that are available in the design. All these clocks are available there. And what is the frequency and what is the period of the clock? And all these things are explained to you. Everything is mentioned for the SoC. Here you can see what are the clocks, base clocks. And these are the clocks which are required on the hard processor system side, which is on the DDR, which is the high frequency designs, right? Wherever you wanted to use on the SoC side, we can use that DDR3, right? And you can see the entire clock summary. You can easily understand from yesterday's discussion that we had only one clock, but now you can see that how many clocks are there and which are the base clocks, and the clocks which are showing generated are the clocks which are generated from the base clocks. Okay. Now we can see, is there anything related to the timing, report timing, and then say setup analysis, go to report time. Right, you can see that it shows this is the thumb node and this is the to node. Okay, which is the launch clock and which is the capture clock it is showing. And here you can see that what is the data arrival time and what is the data required time. So required time and the arrival time, flag is positive. Right, and the same could also be done for the hold analysis. Go to tools, or you can just try from here itself. Report timing, select hold, and say report time. Now you can see that the arrival time minus required time is also a positive. You can see that in the earlier discussion, we developed the RTL code. We copy pasted from the lab manual. And for that code, we have seen what is happening in the timing analysis. But in this design, what we are trying to do, there is a golden hardware reference design, which is an embedded system design using the HPS and FPGA. We have seen how the communication happens between FPGA and HPS. And we have also seen that what happens in the platform designer. We generated the HDL. We instantiated the design in the Quartus Prime design software. We performed analysis and elaboration, compiling the design. And we also have seen what is available in the FSM, finite state machine. We also have seen timing. So only one step what we are not doing is we are not implementing the design onto the board. Other than that, all the steps, whatever required for yesterday's discussion, everything we have done today. So the easiest way is like you have the design already available in the Terasic website, which is called as the Golden Hardware Reference Design, which you can also take it from Rocket Boards. And I request you to complete the entire flow, what I have shown right now. So I will share the lab manual with you. And in the lab manual, it is available only till dividing that into HPS resource as well as the FPGA resource. It won't have any information on the timing and other things on the FSM. I request you to include that also and ensure that together you are able to see that. Okay. And now, for example, you want to get some more information about the timing. So you go to the reports and then you can see custom reports. There are multiple other reports that are available. You want to get a clock histogram. You can provide any one clock. You can select any one clock from here and you can see that what is the histogram. Here it shows that what is the slack value and how many number of timing paths are there in this slack. All these information are shown. Right. So there are multiple options that are available. But, I request you to go through this and get an idea like what is happening in the timing, because timing analysis itself is a big task for you. Right. The one good thing is like there is no violation in the design. And you can also get this information from here. The worst case hold slack is what? And worst case setup slack is what? That itself shows you it is a positive number. I will close this and we will move on to the next important topic. Right. So what is the logic here? What we have done is we have taken an SoC design, which is available in the GHRD. And we have gone through the platform designer, integrated with the Quartus Prime design software, compiled the design. And we have seen what resources are taken on the HPS section as well as on the FPGA section. And we have noted down the FSM. And also we have seen what is happening in the timing analysis and whether the slacks are positive. Right. Now we need to enter into another important concept called as debugging technique. So what is very important here is like you have the design, but how are we going to debug, which is called as the on-chip debug. Now, the earlier cases, when we say that I'm going to debug, right, it is just a kind of simulation, right? We are going to check the functionality by using, right, the model sim, or we can use Questa, Intel FPGA Starter Edition. But here, what is very important is once the design is implemented onto the board, how do you know that it is correct or not, right? It is providing the same functionality. What is the kind of on-chip debugger that is available with the Quartus Prime design software? That's the specific session. I will show you two demonstrations in this, two examples, which are very critical and important for you to understand. That will give you a fair idea on how debugging can be performed. Let me enter into the details now. The Quartus Prime debugging tools are available for NIAS as well as for SoC system. So the debugging tool, what I'm going to explain to you right now, this can be used for a NIAS-based system, and this can be used for an SoC system also. It could be used for both cases. So the Quartus Prime debugging tool is available for all NIAS as well as SoC system. What are the two different debugging tools which we are going to go through is, the first one is called as the signal tap logic analyzer, which is called as the integrated logic analyzer or embedded logic analyzer. And you have the second one, which is called as the system console. So I am going to explain both signal tap logic analyzer and the system console concept. And I am going to walk you through a lab where we are going to see how the signal tap logic analyzer and the system console are integrated in a single example. After going through that, you can recollect that yesterday we have done a memory design where we have created a memory initialization file, right? But then we stopped till there. Today, what I'm going to show you is, first we are going to simulate the design and we check the output in the model sim, but we should implement the design onto the board. After implementing the design onto the board itself, right, we are going to use the on-chip debugger and see whether it is providing the same output, right, on the board also. That is the kind of experiment we are going to see. In both cases, you will be getting a clear picture on how the debugging tools are effective and how they are helpful for us. Let us start with the first debugging tool. The objective of this session is to understand and select appropriate debugging tools for FPGA design. So first thing is, you have the actual hardware, signal tap logic analyzer, and the system console instrumentation. Let us try to do that one by one. First, let us start with the signal tap logic analyzer. What is this called as an? It is an embedded logic analyzer, which is called as an ELA. What is this signal tap? Let's get into the details. Why signal tap? Right? The advantage of signal tap, it easily monitors the signal using simple to elaborate triggering schemes. And no external equipment required. So it is not, we are not going to use any external equipment, no probes, right? And don't need to figure out stimulus since it is based on the actual hardware. You don't need to pass any stimulus because we are going to see what is happening on the actual hardware. That is the greatest advantage of using the signal tap logic analyzer. Okay, what is the drawback? That's what we should also understand. What are the cons when you say? It uses up to lots of memory resources inside the chip. So since you are going to use the embedded logic analyzer, which is an IP, right? You are going to bring that IP into your design. That IP will take some resources. It is going to take some memory resources. Because of that memory resources, what will happen is it won't affect the functionality. Your design will still work like the same design, but the drawback would be it will affect the timing of a design. So it uses up to lots of memory resources inside the chip. Because of that, it can change the timing of a design and it requires recompile, which takes time. So after integrating the design, right, that means after integrating your embedded logic analyzer to the system, you need to again recompile the design, right? Or any modifications you do or any change you do, you have to recompile the design, which will take time. That's the only drawback. But what are the advantages? That's what is shown here. Assuming that when you are using an external logic analyzer, right, what are the advantages? You can do system level debug. You can store large quantities of data and you can do flexible trigger condition, right? You can see that you use an external logic analyzer, then you can perform all these advantages. But what are the drawbacks is, the signals must be physically accessible on the board by a probe. You need to connect all the signals by a probe. And if you need a new signal that is not accessible, then you must make a new board because you don't know how to connect it, right? And the equipment is definitely expensive for the hobbyist. Okay, so somebody cannot spend that much amount for the external logic analyzer. But what is the advantage of using the logic analyzer, which is inbuilt, which is called as an embedded logic analyzer? That's what we are going to see here. Now you can see that the entire logic analyzer is built inside the FPGA. You can see that. What is the advantage when you say the signal tap is a logic analyzer made of available resources inside the FPGA. The greatest advantage is it is going to use the resources which are present inside the FPGA. So it uses available logic elements to implement the logic analyzer, number one, and it samples on-chip signals on the rising edge of the specified clock signal, and it views the captured data through the standard JTAG connection typically used for programming the device. The only difference is that we have to connect the board, right, physically to the system when we perform the logic of signal tap logic analyzer. Right, only drawback is what? It has to be configured via JTAG. So without the board, there is no point in saying that I will perform on-chip debug. That's what is explained here with the help of the signal tap logic analyzer logic. Okay, how do we do this? When you say what are the pros? The greatest advantage is we can tap signals very deep in the design. No unassigned IOs or routing needed. And it comes free with all versions of Quartus. Therefore, no external test equipment required. And we can tap new signals with the same board by reconfiguring, recompiling, and reprogramming. We don't need to do respin. That is the greatest advantage. What is the drawback? It requires additional device resources. And generally, it won't change the functionality, but there is a change in the time. And what is another one? Must have an active JTAG connection. So you should implement the design onto the board, and then only you can check with the help of the signal tap logic analyzer by performing an on-chip debug what is happening inside the design. Okay, how do we do signal tap? When you say, you can see that you require the Altera FPGA device where you have the JTAG hub. You need to have the USB blaster, then you need to connect the board, right? So that means there is a PC which is having the Quartus Prime design software, and you have a signal tap tool, connect the USB blaster, and then we need to connect it to the device. Right, where do you get this signal tap? There are two ways. While creating a new project itself, you can select, yesterday we selected a memory initialization file, right? You can recollect that. Exactly the similar way in the verification or debugging, you can see signal tap logic analyzer file. You have to click this file. Okay, and you can add that in your design. Second thing is, you don't want to do that. You can directly open the IP catalog. In the IP catalog, if you type signal tap, you can see the signal tap logic analyzer is available. You can add those signals directly to the RT. In both cases, it will help you out to solve the problem. Okay, what is the specific demo now? I will show the background and let us get into the details of that tool demo. Right, let us start with this lab now. I will open this lab and then let us get into the details here. So this is the lab which we are going to see, utilizing the FPGA internal memory architectures. So you can see that in yesterday's discussion, we had a memory in which we have just used that memory as a single port RAM. Okay. Now today, the concept is you have a simple base design which has two on-chip memories. It has dual port RAM, and then it also has a ROM. And this dual port RAM has two address ports. It has an address port, read port, write port, everything. And what is very important for us is like you have a DP RAM, dual port RAM, where you have the write clock, and then you have a read clock, and then you have a write address, and then you have a read address. And which address it is reading, you can easily identify by using the up counter and a down counter. And you can see the PLL, which takes the 50 megahertz clock and converts that into 25 megahertz for one and 75 megahertz for another clock. Right? And you can see that there is a ROM, which is a read-only memory, which uses the concept of the memory initialization file, where while performing simulation, you will come to know whether it is reading the data, what is specified in the MIF file. So this is the kind of example we are going to do now. But we are not going to stop with the implementation of the design onto the board. What we are going to do is we are also going to continue this lab with the help of the signal tap logic analyzer on chip debug. So let us continue that here. Now, what is the basic process is the ROM is initialized with data that will dictate what goes into it. So that means you can see there is an adder and the right enable signal to the dual port RAM so that you can see that what is happening. And you also have up and down counters, which will tell the dual port RAM which address to read and which address to write at two different clock rates. There are two different clock rates for the dual port RAM. We have the up counter and down counter, which will intimate to the dual port RAM to which port we have to write the data, from which port we have to read the data. So all these informations are available in this design. Okay, now what is the basic logic? We need to continue with this project, but all the steps are same like yesterday. Only thing is we also need to debug the design in detail. So the first debugging lab which I am going to show you is based on the Max10 device. And the second one is on the Cyclone 5, which is called as the SoC debug. How do we do that with the SoC devices with the help of the on-chip debugger? Let us try that example here. Now, let me open this design and then we will follow the steps one by one. Where is the lab? We can open this lab from here. Go to the C drive. Create a folder. Debug Max10. Inside this debug Max10, use this lab1 on chip QAR file, which is the Quartus archive file. Now go to Quartus. Click open project. Go to C drive. Click here debug Max10. Inside that, select the lab1 on chip.quartus archive file. Save open. Keep the file ready now. Okay. The moment you open with any of the project file, the first information what we are supposed to do is we have to launch the IP upgrade tool. Keep that in mind. So click this launch IP upgrade tool. Automatically, it will ask you that can I perform automatic upgrade because it was created in the version 17.1 and we are trying to open this in 18.0 or 18.1. So click here perform automatic upgrade. Okay, now you can see that it shows that double click to upgrade the IP core. Okay, so you don't need to touch anything, but you should click that and then add. Okay, all the options here. Just click that. And you can see that this is the up counter. You can see that up counter is available and it shows that it is up only. That's what is selected direction. And what is the size is 8-bit. You don't need to change any of the parameters here. Just give next, 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 right? And then finally you give finish. That's all. Okay, it is done. Now you can say close. Okay, now once the IP is upgraded, let us follow the steps. Now, what is very important at this junction is we need to add the dual port RAM. Okay, in the IP catalog, yesterday we selected RAM single port. Today we need to select RAM dual port. Open the IP catalog. In the on-chip RAM, select the RAM 2 port. Double click that. And what should be the name is DP RAM, which is called as the dual port RAM. And select Verilog as the template. IP variation, say OK. Now, what are the operations that need to be performed and what are the options that need to be selected? We need to identify. It is data 7 down to 0, 8-bit. And you can see address, write address is 4 down to 0, 2 power 5, 32. And read address is also 4 down to 0. So 32 words. And since data is 8-bit and you can see the Q is also 8-bit. Okay. Now, logically here, you need to select with read and write, with read port and with one write port as a number of words. As per the specification logic, what is very important is you will have one read port, it is correct, and you will have one write port that is selected correctly, and whatever is that based on the number of words. Say next. And you wanted to change the data bits, right? You can just change it. For example, instead of 8, I want to change this to 9. You can change this data bit, whichever logically you want. And this is very important for you to note down. Either you can select what kind of memory block you want. Otherwise, by default, it will go ahead with the 9K block only. That's what I mentioned in detail yesterday. Okay, now you can go back to this. Select this logic. And you need to use dual clock because you will have 2 separate clocks, right? And then read and write clock to ensure that that is available. Okay, right. Let's go back. Okay, next, dual clock. Use separate read and write clocks. And say next. Okay, so you whichever logically you want to add, you can add that. And then say next, right? And then you need to add the memory initialization file. Otherwise, you can just say next and then finish it. Okay. Now, what is very important for us to know now is the ROM lookup. So, as I mentioned yesterday, how do you create memory initialization file? Today, we can see that in detail, how that is created. And how do we read that? Also, we can get into that. So, go to the C drive and open debug, max 10. Go to the restored file. And here you can select the rom.mif, which is the memory initialization file. So what is done here is from 0 to 63rd location, 322 is the number that is stored. From 64 to 126, 66. And from 128 to 191, 323. And from 192 to 255, 0. So this is the memory initialization value that is provided here. We have to check while performing simulation, are we getting the same answer? And the same, we have to verify it during the signal tap debug. Keep that in mind here. Okay, close this. Come back to the lab, and we have seen that what is the value. We have to simulate the design. While simulating the design, you should have the test bench. Okay, the test bench is already available, which is DPRAM, TB_DPRAM that is available. You need to select that, and we can perform the test bench operations. Exactly same like what we do, right? Let me do that and show that to you. Go through the Quartus design. Say yes. To perform analysis and elaboration. Okay, now we performed analysis and elaboration. Now what we need to do is we should perform simulation. How do you do that? We should go to tools, say run simulation tool, and say RTL simulation. Now open model sim. Okay, and then say do wave.do, run the wave file. Give the do file. Execute the file. Now you can zoom it and see, right? Now what are the values you can see that? So it's better that you convert all the radix to unsigned, whatever. Now you can see that what is the value that is available. Now you can see that. This will give you a clear picture. Right? What is the value that is available? The same value is available in both ports. Right? You can see here it's 113. Here it is 113. So 111, 111. So you can see that both clocks are at the same frequency. Right? And what is the value that is available? The same value you can see in both the ports. Both informations are provided here. Now, during the simulation, we have the guarantee that, okay, what is the data that we have provided, whether we are able to get the same value. That is fine for us. But in yesterday's discussion, we did the simulation and we did synthesis and we did placement and routing. Then we implemented the design onto the board and stopped. But we didn't proceed further. But now what is the necessity is, what is the guarantee that when the design gets implemented onto the board, provides the same answer, right? Because we have a memory initialization file, which has all the values in the specific locations. Whether it is able to provide that value or not, that we have to check. So you can close model sim from this place and we can continue till the programming. So what is the step you need to follow here is, we have done this now, right? And now you need to program the board. So before programming, we need to perform compilation, the entire step. And then we will have the SOF file, which is the SRAM object file. And you connect the board and then program it. After connecting the programming, right, that means after checking the output, you should use the signal tap logic analyzer and see whether it is providing the right data or not. This is the specific logic which we are going to check now. Okay, let us do the steps one by one. Go back to Quartus and let us perform the entire compilation of the design. So once the design is getting compiled, I am connecting the board so that we can perform the programming as well as we can see what is happening in the signal tap logic analyzer. You can see the design has how many number of logic elements, how many number of registers, how many number of memory bits. That itself will show you that how many number of timing paths will be there and how are we going to ensure that the design is meeting timing, right? Okay, functional verification we have done first step. Now we need to check the on-chip debugging. And third, we can see the timing analyzer also. Okay, let us do that one by one. Now what we need to do is, we have seen that there are two ports, dual port RAM. If you go through the schematic, you will get a clear idea. Go to tools, go to the netlist viewers and then RTL viewer. So this is the PLL. And then you can see up counter, roam, down counter, adder, DPRAM. All the blocks are available here. And you have the 50 megahertz clock that is given to the PLL. From there, you need to get two clocks. One is 25 megahertz. Other one is 75 megahertz. Both need to be generated and sent to the corresponding blocks. And the input side, you have 10 switches. And the output, you have 10 LEDs. All are provided the details here. Right? You can see which switch will get changed, and then we can see what is the output on the LED. So you can see the entire block diagram exactly suits what is shown in the lab manual. Right, now let us do programming. Go to the last step now, tools, and go to programmer. Let us program the design. Okay, so what is important for you to check here is when you reach this programmer, you have to see the file, right? And then you can see extension is .sof file, the SRAM object file. And you can see that the program or configure should show the tick mark, which shows that it is ready for programming. Click here, start, and try one more time. The moment it shows 100% successful, now we can come back to the quarters and then we can see what happens in the signal tap logic analyzer. So let us try that now. Go to the quarters main window and go to the tools. And you have to select signal tap logic analyzer. You can see that earlier we have seen tools, run simulation tool, tools, timing analyzer, tools, chip planner, tools, netlist viewers, tools, programmer, tools, IP catalog, tools, platform designer, tools, options, everything. But now what we are seeing is tools, signal tap logic analyzer. Click that. It opens the signal tap logic analyzer. Now you can see the data. What is available here? What is available in the down counter? What is the data out that you can see that? What is the write value and what is the read value? You can see that. The data what is sent that is available. If you wanted to get more details, what you can do, you can drag it here and see that what values are read, starting from which location. Okay, so what is the data out you can see. In that specific location, what is the data that we can see? Now this clearly shows that what is the output. You wanted to run this and then check the output also, it is possible. Go to processing and say run analysis. Okay, you can run for some time. Click again processing and say stop analysis and you can see the data. So now you can see that 66 is the data that it is showing, right? Now we can easily trace out what is this 66 by going through our lab. So here if you could go through that, what is the data, right? You can see that 66 is the data because it is between the location 64 to 126. So between 64 to 126, what is the data? Between 192 to 255, what is the data? Is 0. So it is showing 66 and 0 between these values. Then you can run for some more time and you can see that what is the data it is generated. This clearly shows that what is the data that is available in the design, right? You can just go back again and say run analysis. And then you can go back to processing and say stop analysis and then run for a long time. So this will give you specific data what is up. Right, so now what we did is we didn't stop the design with simulation. We continued till simulation and we performed programming the device onto the board. And the last step is we observed the output in the signal tap logic analyzer. Because in the signal tap logic analyzer, what is happening on the board, that we can see that. Right, so each and every case we can check that. What is the output? What is the location? What is the output? Right. Now let us move on to the second debugging thing. we have seen the signal tap logic analyzer, but this signal tap logic analyzer shows you what is happening inside the waveform, right? Inside the board, right? What logic is happening? That on-chip debugger we can see with the help of the signal tap. What is another important debugging tool that is available is called as the system console. Why it is important is when it is a embedded system, right? We have multiple devices, and it is very tough for us to understand that between the read and write. Okay, if any data exchange happens, what is the data that has been read and that has been written in multiple devices? It is very tough for you to identify. In order to solve that problem, right, we have the Quartus Prime design software uses a system console. What is that? I will explain now. What is the system console? When you say the system console helps you to extract away the complexity of weaving digital waveforms, because it is very tough for you to identify from the waveform which signals are there. For example, if it is a small design, we will have only 4 signals, then it is easy for you to trace out. But when it is an SoC, then you will have multiple signals, right? It is very tough for you to find out by going through the waveforms what is the output. And the advantage is it is super handy for reading and writing the memory mapped elements. And we can insert and compile once. Everything in memory map is settable or viewable. We can see that what is the value that is available in the memory. Okay, only drawback with this is you have an odd syntax because you have to use the tickle syntax with the system console. That's the only drawback. Otherwise, it is a very good debugging tool that could be used. Okay, how it is going to help us? Let us move on to that now. In the earlier design, I showed you a platform designer logic, and then you convert that into an HDL and you take it to the Quartus Prime design software, right? And then we generate the HDL, and you can see that the base address, the end, all the system contents are available in the platform design. What is very important for us is if you have a typical embedded system like this, which has NIOS, this is what we did yesterday. We have NIOS, we have on-chip memory, we have JTAG UART, we have switches, we have buttons, we have LEDs, and then 7-segment displays. All are available. And we wanted to verify what is available in this embedded system. That means what is the exchange happens between any device using the Avalon interface. So how do we solve this problem? When you say we can solve this problem with the help of the system console. System console allows you to see what is in any memory location in a platform designer system at any point of time. So in a platform designer system, what is available at any point of time can be found by using the system console. That's what I'm going to show you the lab demo 2, where I'm going to integrate both the signal tap as well as system console in a single lab. So which will help you to get an idea of what is happening inside the design now. So this gives you the specific logic where it helps you a standard platform, enables reuse, reduces time to market, and eases verification. Right? And how do we open system console? It looks like this, and you need to use the tickle console here and run the tickle script so that we can see what is happening inside the design. So it is an interactive tickle console, and it is a quick system level debugging tool that is used with the platform designer systems. Okay, how do we use this? What is the example? I will explain that to you in detail now. Let me walk you through that example here. I will close this design. Right, now let us go back. Right, open this design where you have the signal tap demo, right? This is what we are going to use, which is the Quartus archive file. Copy this, take to the C drive, and say, you can say debug, but you can say signal tap STP as well as system console SC. Okay, so we are going to do both in a single design. So just paste that single tap demo.qar, and open the C drive, debug STPSC. Okay, so close this project. Click open project, go to C drive, debug STPSC, select the signal tap.quarters archive file. Okay. So once you open this file, what we need to understand from this example, I will explain that to you in detail now. There is a 32-bit scratch pad register available in this design. So what we are going to do is, during the reset, the scratch pad register will have the value as 0. Now, during the write operation, we wanted to write some data into the scratch pad register. During the read operation, we wanted to read the data, what is written in. That's what we wanted to see, right? And what is the data that we are writing that we need to see? And during reset, it should show the value as 0. So what is it is written and what it is read, both should be shown. And then to see that, we use the JTAG master, which will be helpful for us to check the data availability with the help of the system console. So this is the instantiation we have done inside the design. Okay, now what we are supposed to do is, first we should understand what is present inside this design. I will explain that. Parallelly, I will perform compilation of this design. Let it get compiled. Now we can go to the drive, go to the C drive, go to debug, and open the restored file and understand what is there in the tickle file. In the tickle file, what we are trying to do is, you can see that there are two registers, like you can see register 0, right? And you can see there is a procedure which shows that the reset, right? You wanted to see that what is the value that is present in the scratchpad register. First, it is going to read what is the data. During reset, what it will read? It will read 0. And what we are writing inside the scratchpad register after some time is 0x hexadecimal ABCD1234. We are writing the data as ABCD1234 into the scratchpad register. And after writing the data, we wanted to see whether we are able to read the same value. So first read, it will read 0. Then we are writing ABCD1234. And then again, it will read that data. What we wanted to check is during reset, whether it is showing 0. Then after writing ABCD1234, again we are going to read it. It should show that instead of 0, it should show ABCD1234. If that is showing in the system console, and if that is getting updated in the signal tab, that means we can clearly come to a conclusion that what is happening on inside the chip. That value we can see in the on-chip debugger. So how do we prove that? Okay, that's what is this example here. So let me minimize this. Let it complete. Meanwhile, I'll connect the board. So just give me a minute. I'll connect the board and then I'll show you what is happening inside the design. Now it shows 100%. What we are supposed to do is first let us go ahead with the signal tap. Okay, go to the tools. Right before that, you let us program it. Okay, first let us program the design now. So go to tools, go to the programmer. Now, since it is an SoC FPGA device, what it shows here is only FPGA. It does not show the HPS here. First, we need to add that. How do we do that? Is click this auto detect. Okay, it will ask for the device. Okay, so I can select the device here. Say okay. Say yes. Now you can see Cyclone 5 HPS. This is the hard processor system, and then you have the FPGA. Right now, what we need to do is now we need to program and configure. So select the device, configure it, okay, and then you can rerun that. So first, what you should do, select this device, go to edit, and go to change file. Select your SOF file, say open, so that it is ready. So that you can see inside the output files folder, you will have the signal tap demo.sof file. So click here, program or configure. Now you can say start. Now it shows 100% successful. Now we have programmed, but our demo is not getting stopped with the programming because we need to do SoC debugging, right? So what we are supposed to do is we have to see what happens on the signal tap logic analyzer, and we should also see what happens on the system console. So we can minimize this, go to tools, and then go to signal tap logic analyzer. Exactly same case like what we did earlier, we can try that now. So go to processing, say run analysis for some time. And again, go to processing and say stop analysis and see the output. If you see the output, it shows that everything is 0 because during reset, what is the value that should be read if you say that it is showing 0? That's what is shown here, right? Now, what is our next thought process is we wanted to see what is happening in the next stage. So what we need to do is after running the system console, is there any impact on the output? Let us see that. So now it is showing 0 during reset. Okay, minimize this. Okay, now what we need to do is go to the tools and you should select the system debugging tools because system console is a system debugging tool. Go to tools, system debugging tools, and click system console. Okay, once we select the system console here, how do we run the tickle file? When you say it, the command, what you should do is the source. Okay, before that, you see that whether you are in the current directory or not. You are in the correct directory here. Now you say source and say reg_access.tcl. Give that. And now it shows that during reset, the scratchpad register is showing 0. And what it is writing is, it is writing ABCD1234, writing scratchpad register. And it shows that 0x ABCD1234. Okay, now the value is written. Now you can minimize this system console. Come back again to the signal tap logic analyzer. Go to tools. Go to the signal tap logic analyzer. We are in this place. Now go to processing. Say run analysis. And again go to processing and say stop analysis. Now you can see the data has changed. ABCD1234 head. The data what is written, the same data it is able to read also. So this is the advantage of performing debug. Okay, so the debugging demos I have shown in 2 phases. One debug demo I showed with the Max 10 device with memory what is available in the memory content with the help of the memory initialization file. And the second demo is for the SoC FPGA device, where we have written some data in the scratchpad register, and we wanted to see whether the same data is being read when you modify it dynamically, right? When you change something in the system console, whether we are able to get that data again, that change is happening in the signal tap logic analyzer or not, that we cross verified. So this is the debug logic. So I'll close this. You can close this main window. If you want to save, you can say save. If you don't require it, you can say no, so that it can close the entire design without saving the portion. All right, now let us move on to the next important topic, which is called as the high-level synthesis. Let us move on to that. Debugging techniques are shown to you now, but it is very critical and important for you to understand what is available in the logic, right? Are there any questions in this place? How to include debugging signals and check the response? Okay, so that's right. So you can add those that with the help of the STP files that is available. Okay, so that's what I showed you right now. So what you can do is you can use that as an IP. So open the Quartus, and you can see in the right hand side that you can see there is an IP catalog. Type here signal tap logic analyzer. It will show you Altera signal tap logic analyzer. Double click that. And you can see this is the IP parameter editor, where you can add all the parameters that are required. So here you can add whatever trigger you want. So you can see the create IP variation. And now you can say that it is unnamed. For example, you wanted to say trigger one something, whichever name you want, and what is the device, right? That you can select it and say okay. Now you can say what is the data input, what is the sample depth, what is the RAM type. Okay, all the information for the data, and you can also provide that for the trigger. So after doing this, you can generate that HDL and that you can include STP file, right? That is also possible. Right, you can finish this and then that could be taken into account. So here you can use this, or else you can go to File, New, and go to Signal Tap Logic Analyzer file. Select it and save OK. Now you can see there is an STP file created. On the right hand side, you can see what is the clock, what is the sample depth. So you can use it for data as well as for trigger operations. All the information are available for trigger. You have AND, OR, comparison, advanced, everything is there. Now what you can do is after selecting everything, you can say file, save as, and it will be saved as a .stp file, which is called as the signal tap logic analyzer file. You can save this file, and what you can do is this file, you can include it during your while programming. Okay, so that is also possible. So what you can also do is in the settings, right, while creating the options, right, you can go to options, and then here you can see EDA tool options, right? So here you can see what kind of logics are available, and based on that you can add those things. Are there any other questions? I feel. Yeah, you can directly download, right? So that you can directly take that as a print screen, or you can just copy that into the PDF or Word, right? So image processing, image vision is there, like which we can do that with the help of the AI logic. So otherwise, I hope everything is fine. Right, let us go to the next topic now. So this is a very interesting topic which we are going to discuss now, because in all other topics, either we were developing the code or we were utilizing the IP catalog and generating the HDL, and that we have incorporated. Now, in this case, what is the basic thought process is, we wanted to ensure the code what we are developing, right? And what we are writing that in the software, that need to be converted into an RTL. That means you are going to convert a high level code into an RTL. So we call this as a concept of high level synthesis. So we are going to understand the concept of high level synthesis, and we are going to understand the Intel HLS compiler. That is very important for us to understand at this junction. And how do we functionally verify that? And we take that IP for Intel FPGA, and we can also understand how the component executes on the. Okay, so there are 2-3 slides I need to explain to you before we enter into the lab. Why high level synthesis? This is very, very important for us. Why HLS? When you say Verilog or VHDL are hardware description languages, they are not algorithmic in nature. Using C++ instead of RTL as the primary design entry language enables engineers to focus on algorithmic level optimization. That means if you are trying to write a code which includes the compute intensive algorithms, where a kind of decoding or encoding algorithm or image vision, then it will be definitely time consuming for us to develop the RTL. So in that case, what is mentioned here is, we can use C++ instead of RTL as the primary design entry language, which will enable engineers to focus on algorithmic level optimization and less on time consuming hardware level optimization. And then the designers can then execute the FPGA component as a C++ program on a CPU. And what is the greatest advantage is C++ level execution enables verification that is of orders of magnitude faster than RTL simulators. So it is very, very essential that we can come to a conclusion that we can enable the verification faster than how do we do that with RTL. What is the flow here? So for the past 2 days, the flow was you write Verilog code, or you take the IP and take that to the Quartus Prime design software, generate the binary, and then we implement the design onto them. But what we are going to do now, you have a C or C++ code that will be taken to the HLS compiler, and that will generate the Verilog code. That we will take it to the Quartus Prime design software, and then we will generate it. So C or C++, ease of use, FPGA quality of results, and partnerships and ecosystem. Right, so that's the flow. So you take the C or C++ code, take it to the Intel HLS compiler, and convert that into Verilog code, and take it to the Intel Quartus Prime design software, implement the design onto them. Okay, so how we can do multiple flows here? So you take the C and C++, take it to the HLS compiler, and either you can directly perform instantiation or platform designer, or you can take it to the programmable acceleration cards, which we have a pack card, or you can go to Intel FPGA SDK for OpenCL or OneAPI. So our main interest is we can take it to the Quartus. That's the flow which we are going to do now. Okay, what kind of applications requires high-level synthesis? This is very important for us to understand. Any AI or ML applications, ultrasound, high performance computing, codec, or compression requires the algorithm which requires the high level synthesis compiler. And industrial applications like vision sensor, motor control, smart city or IoT applications, ADAS, right, as well as military and wireless or 5G applications. In all these applications, we need to utilize the high-level synthesis compiler. What is happening in a design? It's like where we require the compute-intensive algorithms, where it is easy for us to write the code in terms of software, and it is very easy for us to convert that into an hardware. But then whether it is going to give you the same kind of efficiency what we get in the HDL, right? That is the kind of question mark. So what is the goal now when you say? Okay, thank you. Right. So now what is our objective is, you take a C or C++ function and we need to convert that into an RTL implementation. Then we need to do that. First thing is we should develop the component in a software environment and we functionally verify the component within the software environment and seamlessly integrate that with the hardware simulation environment, and we optimize the design and we integrate that IP with the traditional FPGA design tools. This is the flow which we are going to follow. But whether it is advantageous, that's what we are going to see. I'll just show you one small logic, right? This you will get an idea. What we were doing for the past 2 days is we need to develop the code. We perform analysis and elaborations. We do synthesis, we do filter, assembler, then we do timing analysis. Then we need to perform hardware debugging. Till now I showed you this programmer, signal tap logic analyzer, signal probe, everything we have seen now. Now what is our thought process is, this is a potentially time-consuming effort because you should write the code, you should perform behavioral simulation, we should do synthesis, then we should perform placement and routing, we do timing analysis, then we should achieve timing closure and take the design to FPGA. But how do we solve this problem? That's what we are going to see that now. For that, I will show you a simple logic here. You take the HLS compiler, which will generate the RTL. You can perform RTL/C++ test bench or core simulation and import that RTL to the Quartus. This is what we are going to do. And it is very easy for us to review the reports and performance. And we can view the bottlenecks, graphical and hierarchical. Both are possible. Okay. But is that providing you the similar kind of results when you say, yes, what is our goal we can see? That's what I'm going to show you here. So you take the C or C++ code, take that to the HLS compiler, convert that in IP and take it to the Intel Quartus Prime design software. We want the same performance as hand-coded RTL with 10 to 15% more resources. That means we are going to get more resources, but what is very much required for us is, are we getting the same performance? That's what we wanted to check. So what is the goal now? We need to get the same performance like hand-coded RTL, but it can take more area. That means 10 to 15% more resources it can take. Okay, what is the process? You take the C or C++ code, take that to the HLS compiler and convert that as an IP, take that to the Intel Quartus Prime design software. Okay. Only thing what is required along with our Quartus tool is we should have a standard GCC or C++ compiler. So this is the one which we are going to use, which is the Visual Studio. That's what is sent to you, right, in the link. Okay, if you want, I can show that once again how to download it so that you can integrate and run the lab example. Okay, how this could be done right now when you say, so this is the link which has been shared with you. So you need to enter into this. Okay, just give me a minute. Okay, so just see whether it works. Otherwise, you can just check that directly. Okay, here you have to, once you reach this page, you have to download this Visual Studio Professional 2010. Okay, on the right hand side, you can see download. Once you download this, you will have a setup file, and you can just double click and then install that setup exe file. Okay, these are the two steps. One, you just download this Visual Studio because this is required for the first step. We have to take the C++ code and we need to run through the GCC compiler. Okay, for that, we are going to download the Visual Studio Professional 2010. Okay, so don't try to download the latest version because the latest versions may not be compatible with what is the Quartus version we use, right? That's what I'm giving you the correct link so that you should not get confused. Okay, once you download, what will be there inside that I will show you. Before that, let us go through the lab. What is available in this lab is we have a C++ code, which is the floor square root.cpp. So I will just show that to you now. So this is the C++ code. Okay. Now you can see that hls.h, which is high level synthesis, and this specific code is written for finding the square root of a number. So this is based on the HLS Avalon slave component. And when we are developing the square root of a number, this is based on a simple binary search algorithm. You take two numbers and then we find the middle. And based on that, we are going to find out whether it is less than, greater than, and find out which is the nearest square root. We will seal and round it off to the nearest integer. The same algorithm is written here, unsigned integer. Mid is equal to start plus end by 2. And mid star mid equal to x, then we can say return mid. This is the perfect square. We need to floor it. Then if it is smaller than x, then start equal to mid plus 1. We are going to increment it. If it is greater than, when we need to subtract it, end equal to mid minus 1. Okay, so this is the code. And we want this code to be converted into an RTL. This C++ code. And how do you verify this? There are 4 combinations here. What are the test cases you have is x1 equal to 4, x2 equal to 36, x3 equal to 257, and x4 equal to 65536. Right? Other than 257, all are perfect squares. For 257, it is going to give the nearest integer, which is 16. We are going to check that with the test cases. So what we wanted is, we wanted to see this component, what you are writing that as a component, we want this entire block need to be converted into a RTL code. Right? Let us try that, how it happens. Open the lab manual. What are the 2 steps we are going to do? I will show you. Then one by one, we'll try that. So this lab is based on the HLS implementation of a 32-bit square root component. This is what we are going to do now. So that means
because now it's you have to copy and you have to paste new. One thing, the first few steps, which is there.
okay, thank you. So HLS implementation of a 32-bit square root component. The main logic of this example is that we are going to perform HLS implementation of a 32-bit square root component. How do we do that? When you say there are three important steps we need to do. The first step is called as emulation. For performing emulation, you require the Visual Studio 2010, which I told you that you need to download and keep the things ready, right? So emulation is the process which is the functional verification of C or C++ code what you have. Okay, and this is simple. It's exactly like your GCC compiler, which you use in our C or C++ programming. Same. By this command, we are not going to get generated any RTL. It is not going to generate any RTL in this step. Okay, this step is going to check whether your C++ code is functionally correct. That is called as emulation. The second step is called as co-simulation. When we do co-simulation, what is the meaning is, we are going to target C++ code for the corresponding FPGA device. In this case, I am going to target this for Max10 device, right, which is for the Max10. So what is given here in the C++ testbed, we are going to provide which device we are targeting. I++-M, which is the architecture, the microprocessor architecture equal to Max10. That's a device I am going to do. Then we can perform compilation. These are the three steps we are going to do. So if you see the paragraph, you can get a clear idea. The HLS procedure contains three main steps to integrate a C or C++ algorithm down into RTL. The first step is called as emulation, which is the functional verification of the C or C++ code that was written. The second one is called as co-simulation, which generates both RTL and compiler reports, so that you can check the output in terms of simulation. You can also see what is the resources it has used from the FPGA side. Then what is the third step is, you can take that design to the Quartus Prime design software, and you can see that what is the resource utilization and in what frequency it is working. Everything we can check. This is what we are trying to do in this specific lab. So the only difference is, you don't need to develop the RTL. Instead, the code is available as a C or C++. Using our Intel HLS compiler, you are going to convert that into an RTL. Okay. To get more details, you can refer to the Intel HLS compiler page. Okay, you can go to Intel high-level synthesis. Okay, compiler. So go to this page, and high-level synthesis compiler page will provide you more details. So it shows that Intel HLS compiler. There you can see Intel high-level synthesis compiler, which takes the C++ code and generates the production quality RTL code that is optimized for Intel FPGAs. Okay, so you can see what are the features, and you can see the getting started guide, and then you can also get the documentation and support, where you have technical documentation, videos, training courses, everything is there. If you want to see any kind of training classes based on this, that you can get that here. Everything is available in the home page itself. Okay, let us go through the lab now. What we are going to do is, there are three steps. All the three steps I am going to show to you now. One by one we'll try. First thing is, you should have the lab manual ready, right? Second thing is, you should have the lab files. Okay, I will show you both now. What is the lab file here? When you say, you can see this floor square root.cpp and the floor square root.qar, which is the Quartus archive file. Now, what is important is, you should ensure that this particular folder is present in any of your drive. Either you put that in the downloads folder or in the C drive, wherever you want. So inside this, what is available? You have the C++ code, you have the Quartus archive file, and the lab map. The only thing is, what is available here is, the setup.txt file need to be renamed to setup.batch BAT file. Okay, because this batch file cannot be sent through email, right? It will stop. So that's what it is, just renamed as txt. Once you receive this, what you should do is, you have to change this setup.txt to setup.bat as a batch file. All other things are same only. Then you can follow what is available in the lab manual. Let us try this one by one now. First, you should open the Visual Studio. Okay, that is after you install, you can see that in the command prompt, right? You can see that in the start window. So you can see Visual Studio x64 Win64 command prompt. Let us open that now. Type here Visual Studio. The moment you type that, you can see Visual Studio x64 Win64 command prompt. Just open that. Okay. Now, once it gets opened, you need to use this command where you are going to take it to the corresponding folder. So it is available in my downloads folder. You can take this first now, CD, copy this, and then paste it there. What you need to change is username is not username. So I have to put my username. Okay, so I will add my username here. Now it is inside this folder. Okay. Now once it reaches, you have to type the setup.batch file. What this setup.batch file will do is, you have to ensure that inside your Quartus installation, there would be a folder called HLS that you can check that. Okay. So see, Intel FPGA Lite 18.0 HLS is the root of I++. So you can easily verify that is it available. Go to your installation directory and check that in the Intel FPGA Lite 18.0. Okay, you can see there is a folder called HLS, high level synthesis. Inside the HLS, you can see examples. Everything is there. Counter, image downsample, right? Decimation filter, QRD. So many examples are there. Okay, all these examples has the C++ code. You can see that counter.cp. So the C++ code is available. So that this will be taken as a reference, and you will come to know how this could be converted into an RT. So simple logic is given. So go through this and get an idea. That will provide you some more input. Okay, let us go to the lab now. Okay, now what we are supposed to do is, we need to do the first command. The first command is we need to perform emulation. Okay, what is the command for emulation is I++ -mr, the machine architecture is equal to x86 and then 64-bit. Floor square root.cpp, that is a C++ file, -o emulation. If you are not giving -o and some name, right, by automatically it will take, right, everything starts with A, right, but you wanted to provide a specific output, right, you can say -o, and what is the name you follow, the same name you should provide to generate the exe file. Run this now, copy this, and use that here. Okay, now what you should do is emulation.exe. In this place, what happens is, the floor square root of 4 is 2, floor square root of 36 is 6, floor square root of 257 is 16, floor square root of 65536 is 256. That means it is showing in the emulation that the C++ code functionality is correct. Okay, now what we need to do is take that code, target it to the corresponding Intel FPGA for Max-10 device, and then again we should cross verify it is providing the same output or not. Then only it is easy for us to analyze the reports. Okay, now let us move on to the next step. So open the manual and see the next command. We are going to target it for the corresponding FPGA now. Okay, so the step is called as co-simulation. Whenever we do co-simulation, what are the things that we will get? First, we will understand that, and then we can try to see what is the output that is generated. So whenever we do co-simulation, an executable which will run the test bench, okay, that will be generated. And any calls from the functions, right, from the test bench will be a part of the simulation. First, executable will be generated. Second, all the necessary files include the IP in the Intel Quartus Prime design software will be generated. You'll have a QSys file for the platform designer, IP file that you can directly add to the Quartus project, and .v file where you can instantiate your design. You will have a component hardware implementation report, which is estimation. And you will have an Intel Quartus software project to compile all the IP and generate a more accurate report. So we will see the estimation report. We will also see the accurate report, both. Then you will have all these information that are present in a single folder. How do we do that? When you say what is the command? I++ hyphen GHDL, this is for the HDL, hyphen MR equal to max10. So what you need to do, the changes is, we are targeting it for the max10 device because this is a light edition which supports only max10 and cycle 1. But if you are trying to use standard or pro edition, you can target it for ARIA 10, Stratix or Agilex devices also. Now take this now, I++ hyphen GHDL hyphen MR equal to max10 floor square root dot CPP hyphen O course simulation. That is the command. So just copy this here and paste that. Now, once we do this step, it will take 2 to 3 minutes for you to complete this step. So during these 2 to 3 minutes, what it is doing is, it is generating the files that are required for your RTL. It generates the QSys file, it generates the IP file, it generates the Verilog file, which are required for checking the functionality. Okay, so now once it is generated, now what we need to do is we should say simulation.exe. Now after performing emulation and after performing core simulation, you can able to see it shows the same answer. So floor square root of 4 is 2, 36 is 6, 257 is 16, and 65536 is 256. It is done now. Now what we need to do is we can go and check the reports here, right? So now how do we go ahead with the reports? Let me show that to you. Okay. Go to the downloads folder. Go to the HLS quick start source files. And you can see there is a PRG file, which is called as the code simulation.prg. Open that file. And inside that, you can search for the reports. Okay. And then you can see report.html. So when you open this, you can see that it is targeted for Max 10 device. And it is Quartus version 18.0. And what is the command we provided? And what is the time it has generated the report? All these informations are there. What is very much interested for us to see here is, you can see how many number of lookup tables it has taken, how many flip-flops, how much memory, and how many DSP slices it shows. Now you can see that we need to know about the adaptive lookup tables and the flip-flops, RAM, DSP. So it is not taking any on-chip memory, but instead it takes the DSP which are available. Okay, now you can see that it takes 1447 adaptive lookup table. That means it takes 4%. Flip-flops, it takes 5%. And then DSP, it takes 2, which is 1%. Because available, how many you can see now? based on the device. And why it takes so much, that also we have to find out. Okay, so that we can find out in detail from this place. Go to the reports and say summary. This is what we have seen now. Second thing is loop analysis. If you see the loop analysis, you can see that why it is taking, right, this many resources that we have to find out. How can we find out that it is taking this many resources, right? So that we can just check here. See here, it takes 2.7 clock cycles, right, for integer comparison. Line number 28. You can see that line number 28. If mid star mid less than X, that's what we have written. But if it is a normal RTL code, which we do, which is like an hand-coded RTL, generally we will avoid writing block multipliers. We won't directly use the star operator. Whenever we are writing a multiplication algorithm, we will try to use that in terms of shift operators. Either you can use arithmetic left shift or arithmetic right shift, or logical left shift or logical right shift. We will try avoiding using the block multipliers. So since it is a C++ code, you can see that it uses directly the block multiplier. And even the line number 23, if you say, it takes 2.2 clock cycles in order to perform the integer multiply operation, because it is not only just multiply, you have to multiply and then you have to compare. If mid star mid equal to X, so it has to multiply and then it has to compare. So if this need to be performed, it shows here it takes 2.2 clock cycles. And for rest of the operations, it shows 1.7, 1.5, 1.5 like that. We were expecting this to happen in 1 clock cycle, but it shows that it takes 5 clock cycles. The initiation interval, if you look into, it shows it takes 5 clock cycles. And what is the bottleneck it shows, and what is the detail also you can see. The problem it is data dependency. That is the problem. So we can easily come to a conclusion that because of the data dependency, or it can be memory dependency also. In this case, it's a very small design. So it is showing the data dependency. Because of that, it has done. Right? Now you can click this and you can go to area analysis of source. Area analysis of source means in the system, you are able to see that, okay, how much resources it has taken. But what is very much interested for the designer is when we divide that into blocks, right? Which block is consuming how much area? That's what we wanted to know. So now you can see that. Which place it is taking 2 DSP slices? I can take that. So go to 23rd line. If I expand that, this 23rd line uses 2 DSP blocks. What is that 23rd line is mid star mid equal to X is there. So this mid star mid equal to X is taking 2 DSP slices, right? Because you need to multiply and then you need to compare. So which particular segment of the code uses what kind of resources, that information also we could see that by this design. And what is the bottleneck? That also shown, so that if you want to take any action, we can do that. So all this information would be shown in the high-level synthesis compiler. Okay, now let us go through the quarters. What happens here, we'll see. Now say open project, go to downloads, go to the floor square root .quarters archive file. Okay, so now you can see that, okay, what is the specific logic it has been generated. So this is the floor square root QAR file, which is present inside this. Okay, so you can see that it is generated. So just you can run the compilation. For example, you do the compilation logic. So if there are no questions, can you please mute? Yeah, thank you very much. Right, now what is the basic idea is, we have seen this, but sometimes what is very much important for us is, what is the guarantee that it is getting simulated correctly? We have seen that simulation output in the C++, and we have also seen that it is providing the same output in the core simulation. But we can also use the model sim simulator to check out. Okay, so that is also possible with the high-level compiler. How do we do that is, so you can see in the same lab manual, given that information also, so that you can check that. You wanted to check the output in model sim. What we can do is go to vsim. Inside the core simulation, there is a verification project where you have the waveform file is available, right? So just take that. Just click here, say enter. Now it will open model sim for us. So then what we can do now is do wave dot. Now you can see that for the specific design, right? What is the square root? You can see for 36. Okay, what is the square root? You can see it shows 6. You can see that here. Okay, you can see it takes how many clock cycles to predict output also, you can see. So this is the input what you pass and what is the output you are getting. Similarly, you can drag this. Right. So this is for the square root 4. Answer is 2. Right. And then you can see 6, 8, right? All this information can be seen. Right. For the 36. And for 257, which is the square root is 16. We can drag that and see whether it is showing 16. Here you can see the answer is 16. You can see the pulse generates here. Answer is 16. We can see the simulation result also here. Okay, I will close this now. Okay, all the informations are available in the manual. I request you to just go through that and get a detail of that. So this ends once you get the result. Okay, you can compare RTL versus HLS, both, and then see that which takes the area. Okay, that information you can see. This is what I showed you, where it takes how much result, component viewer, and what are the different, right, blocks that is shown to you here. This ends the lab. Right, now you can see that is it taken that much resources what is shown when you say that is estimate. Okay, but here if you see it has taken memory, but it has not taken any DSP resources. But when it was showing in the HLS estimation result, it has used 2 DSP resources, but it has not used any RAM. But in the quarters, it has used memory and it has not used any DSP. But how many logic elements you can see? 1850. And the total number of registers is 1020. But it was showing more, right, in the report. So that was estimation, and this is the accurate. You can see this information here, what is provided. So now you can see that. Thank you. Right now it shows that how many number of logic elements are there and how many registers it is shown, right? But when we look at the same here, right, it was not the same, right? If you see the report summary, it was showing 1447 adaptive logic modules and then 2284 flip-flops it shows. And then it shows 0 RAM, but it showed 2 DSP resources. But when we see the estimation report, we are not getting that many registers. In the accurate register portion, you can see it shows only 1020. Okay. And you can also see the timing information from here, whether it is providing the exact timing information of what we wanted. Go to tools, go to the timing analyzer, create timing netlist, and then report the clocks. You can see there is a clock that is available, and then based on that, we can generate the report. Is that creating the violation or not? We can cross verify and check. So slack is more, we can modify it and then ensure that the design can work. So you can add your own clock and ensure that the design can work at a higher frequency. Right. Now, what is very important for us to understand is when do we need to go for RTL and when do we need to go for HLS? That is very, very important for us at this junction. So because at times we may not be very sure that when do we need to go for it. Okay, so that is very critical and important for us to understand. Let me explain that also to you. I've shown you that what is happening when you develop the code and what is happening when you take the C or C++ code and convert it into an RTL. But this specific logic is also very important. When do we need to go for RTL and when do we need to go for HLS? RTL versus HLS. To do this, I have two important lab logics, and that will give you a clear case study that what is the basic idea and when do we need to go ahead. There are two labs. One is we need to use the Verilog RTL versus the HLS comparison. So the lab one is the state machine stoplight controller, which provides you the exact number of seconds tick away before the lights change. So one is based on the RTL. The other one is based on the HLS. Now what we need to do is one is a finite state machine, example, traffic light controller. Other one is on the multiplier. Now what is very important for us is in what cases we wanted to go for HLS, in what scenario we should go to RTL. So let us first get some feel. When it is a state machine stoplight controller, it is going to work on the clock tick, exact number of clock ticks. Because when we write an FSM, we will ensure that the FSM is divided into 2 always blocks or 3 always blocks. And you write the sequential logic block separately and the combinational logic block and the output logic block separately in an RTL code. When we do that, what happens is you will be getting a traffic light controller like this. And it is very easy for us to code that in the RTL. It takes 120, right? And then when you convert that code into the HLS converted code, if you see, it takes only 75 lines. But the number of resources, if you see, it takes only 10 registers, but it takes 213 registers. ALM only 14, here it is 134. Now the question to us is, why the HLS code is taking more number of registers and more number of ALMs when compared to what we have developed? There are two main reasons for it. The first reason is HLS is C or C++ based, which means there is no precise way to specify cycle accurate state machine like Verilog or VHDL. So there is no cycle accurate state machine like Verilog or VHDL. Therefore, it is definitely tough for us to take the case forward. Really tough. Why? Because since we don't know how to write the code in terms of specifying the cycle accurate state machine, like what we follow in Verilog or VHDL, the only way to solve the problem is writing more number of nested loops. So as a consequence, traffic control in high-level synthesis is only possible with the nested loops and the selection of if-else statements. There are more number of if-else and switch statements that are available. Okay, now because of using this more number of nested loops and if-else statements, what happens is it requires more number of logic and registers to achieve the desired functionality and best performance. In order to achieve the desired functionality and best performance, it is very, very tough for us to do that without the help of the loop. Now you can see there are more number of blocks and more number of loops, and this takes you more number of registers. Okay. Now you can see there are different blocks. In each and every block you can see it takes 18 registers, 50 registers, 40 registers. Now take the second case, which is called as a multiplier, a pipelined multiplier. So this is the basic block diagram where you have 8 32-bit words which works at 100 megahertz, and then we need to have 2 clocks, right? One we wanted the output at 200, other one is in 400. Now this is like a multiplier and an accumulate unit. If this is written in terms of C++, right, what happens will see, and the same we can see that in terms of RTL code. If it is a simple RTL code, we instantiate a PLL and we will generate 2 clocks. One is 200, other one is 400. And based on that, we will perform multiplication. What is the only challenge for the RTL engineer is you have to ensure that how to transfer the data from one clock domain to another clock domain, because one is working at 200, other one is working at 400. So 200 to 400 megahertz clock domain crossing, how do we do? That's what is important. The second thing is, what we also need to understand is, it is very easy to see parallelism with respect to the RTL code. And the same code is written in HLS. And the greatest advantage here is you can use this as a simple matrix multiplication logic, right? And that is going to provide you the similar kind of results, even though it takes more registers. But you can see the performance of the FPGAs. It is trying to give you the similar kind of performance, even though it takes more number of resources. Because with the 4-stage and with the 8-stage pipeline, you can see that it is 325 megahertz, and then it shows here 387.75 megahertz, which is a pipeline multiplier. Okay, what is the conclusion at this junction when you say RTL-based method is best for precise timing? Wherever we use the state machine and control-centric operations, it is better to use the RTL-based method because that will help you to perform precise timing. And it is very easy to control the number of resources and aligning edges in terms of clock cycles. So writing the code in terms of clock cycles is very easy. But when you take the high-level design, where we use the C or C++ code and convert it to an RTL, where do we go ahead when you say the high-level design enables productivity gains for computational-centric problems that involve vector arithmetic. So where it could be used, it is good for video, AI, compression, etc. Wherever we use video, AI, and compression, in all these places, it is better to do high-level synthesis because it is definitely time-consuming for us to develop the RTL, hand-coded RTL. And even though it is not as optimal for area, and performance, but you can get a quicker development. Because at that case, what is important for us is we need something quicker. And we have some specific options that is available, which we can optimize it further. So high-level design is excellent for algorithmic development and analysis, very quick to simulate, and easier to create test benches. And the development iteration cycle improves by 3 to 5 times. That is the logic. Okay, now that is the basic thing. Now what we have seen is we have compared that when do we need to go for RTL and when do we need to go for HLS with 2 case studies. Now the design is very small, like you don't need to write a C or C++ code for a square root of a number. We can do that with specific RTL also. But the idea is like when we try to do that with RTL, what is the time taken, right? Definitely it will be time consuming. Then how do we do that with the help of the C or C++ code? Similarly, a kind of a sorting algorithm, right? A merge sort or whatever sorting algorithm we use, it is very easy to write that in as a C or C++ code rather than writing the same with respect to RTL. Where are the resources that I will show that to you now? You can go through this, get more details about that. Intel FPGAs for AI. So the Intel FPGAs for artificial intelligence provides you the solutions for AI, where you will get more details about what are the resources that are available. Where you can see FPGA versus GPU for deep learning. Okay, you can see resources. And you can also see the resource center where you can get technical documentation, videos, training courses for AI solutions. So the page is FPGAs for artificial intelligence, which explains you in detail where we could use Intel FPGAs for AI. The second important thing which you also need to go through is Intel FPGAs for machine learning. So Intel FPGA machine learning, if you take it, you can see that machine learning FPGA applications Intel. So you can go through this site, which explains more information on the machine learning. This is very critical and important for you to get into that. So you can see that it uses the CNN implementation using an FPGA and an open CLD. This you can get more details. And you can watch the video. And where are the different set of applications? If you see, these high performance computing applications are used in intelligent vision, and then scientific simulations, life science and medical data analysis, financial services, and oil and gas. If you want to get more details about it, you can get information from here. Overview, videos, design, and documentation. So these 2 websites are important for you. Intel FPGAs for AI and Intel FPGAs for machine learning. Right. And we also need to look into the Intel FPGA academic program. So FPGA University, or you can just get into this directly so that I can provide you more details. So fpgauniversity.intel.com. So this will take you to our Intel FPGA academic program. So the moment you reach this page, you can click here, teach and learn. So this is available for the faculties as well as for the students. You can click here, teach and learn, which you can click explore. And this will automatically take you to the teaching materials page, where you can see tutorials, lab exercises, computer system, software, workshops, etc. Now, what is important here is the moment you click this materials here, you can see there are 4 important subjects which you can look into. One is called digital logic. The other one is called as the computer organization. Third one is the embedded systems. Fourth one is the artificial intelligence, which I explained to you now. Now, the moment you click the digital logic, it will take you to the digital logic page where you can get materials of all digital logic designs. For example, simple lab on switches, lights, and multiplexers, numbers and displays, latches, flip-flops, and registers, counters, real-time clock, adders, subtractors, and multipliers, finite state machines, memory blocks, processor. Everything is available. If you are very much comfortable with Verilog, you can download the Verilog section. If you are comfortable with VHDL, then you can download the VHDL section. This is the first subject which you can go through. The second one is on the computer organization. The computer organization subject uses the NIAS2 or ARM. Okay, so I have shown how to create an embedded system design using the NIAS2 soft core processor as well as the ARM-based design. So you wanted to download NIAS2, you can download on the right-hand side, or you want to download only the ARM, that you can take it from. All the examples are available. That will help you to get it. For example, input and output in an embedded system. That shows that the output can be taken in terms of NIAS2, or you can take that in terms of ARM. Right? All these informations are available. You can see introduction to graphics and animation, which shows you the details on ARM or in NIAS2. This is a second subject which you can look into. The third one is called as the embedded systems, which we discussed in detail. You can get more examples, like we have seen 1 or 2, but you will get more detailed examples here. You can see that getting started with Linux, developing the Linux programs that communicate with FPGAs between the HPS and FPGA. Okay. Character device drivers and ASCII graphics for animation. All these labs are available here using the accelerometer. Okay, all these labs are available with the embedded system. And the fourth one is the AI, which I mentioned some time back. If you enter into the artificial intelligence, after going through the digital logic and embedded systems, you can go through the AI. Right here, you can see there are multiple examples. Accelerating computer vision techniques, lane detection for autonomous driving, classification of handwritten digits, and CNN classifier. Right? You can see, you can write, compile, and run a C++ program, and you can use the OpenCL kernel to check out. All these labs are available. And if you wanted more information on the materials, right? So that will also be available. Right? If you go to the overview page, if you click here, tutorials. Okay. If you click this tutorial, in this case, digital logic hardware design. So you can select a version here. For example, this is 21.1, but I want 18. So just click that 18.1. Okay, because the focus of the 3 days is like 18.1, so that you don't need to enter into different set of versions. Okay, select here 18.1 so that you can download whichever example you want. For example, introduction to the Intel Quartus Prime Design software, standard or light. Don't go to Pro. You can download either standard or light, and then click here Verilog PDF. For example, if I click this will download that logic for me, and I will show you what is inside this, right? So you can see that you are very new to Quartus Prime Design software. Like yesterday, day before when I introduced, okay, same, see here, design entry, synthesis, simulation, all those things you do. And then what is the basic logic is, how do you start the design? It is step by step, it is explained. Like how I did that yesterday. You can select the board, which board you want. And you can see that. If you are very much particular about one board, you can see the device name here. right? You can select that. For example, you can easily recollect D10 light. We gave 10M50 DAF484 C70. And we gave D1 SoC yesterday, which ends with F31 C6. You want to work with other boards also, it is possible here. All these informations are given. So this is a simple example which uses an assign statement, and you take that to the prime editor, develop the code, synthesize it, right, and then do pin planning, generate the SOF file, and then implement that onto the board. You don't need to go to the last step, but you can definitely complete till this place. Okay, you can do location and then you can run synthesis. You don't do the last step, programming and configuring. All other steps you can definitely do with what is available right now. This is for the first thing, like digital hardware design. The second information is digital logic simulation and debug, which I explained you. You are very new to model sim, you can take here. You are new to Quartus prime timing analyzer, which I explained you yesterday, then you can take this. Signal tap logic analyzer, which I explained you here, and debugging hardware designs. If you click this debugging hardware designs, this is going to show you that what are the different things. So how it is using is like taking a design, how do you debug the design? Everything it is explaining here. So you can take a design here. Okay, and then how that is verified is explained. And this is on the computer organization subject where it uses the ARM processor and hardware components. If you click this, this will give you accessing the HPS devices from the FPGA. This is the device which I showed you in the lab, right? So you can download this and then you can try this lab on your own. Right? All these examples are available. Right? So you don't require the board for most of the labs. It is easily done till compilation. So I request you to go through this to get into the details. Recommended tutorials are there, whichever required. And then you can see what are the recommended lab exercises also. Right? And the professors can get the solutions. Okay, so that you can get the solution so that you can practice it and then get an idea of what is happening in each and every design. Okay, so this is available here. And I explained you about the Thoracic site, and I also shown you about the rocketboards.org. And again, one more important thing, you should not forget that. So design store for Intel FPGAs or FPGA design examples. Go to this site, this is easy for you. Intel FPGA design examples. So again, go through this page. Intel field programmable gate array FPGA design examples. Go to this particular link. This link will take you to the multiple places. Okay, FPGA design store. And it will also take you to rocket boards. You can click here. This will take you to Cyclone device, for example. I want Cyclone 4. So then you can see Cyclone 4, DE2115. This is one board. I want to get some details. What are the projects that are there? That we can check it here. Or I want ARIA, you can click that. Or statics or Agilex, whichever. Keep that handy. FPGA design for design store is something important. Right. Are there any other questions? Okay. So yeah, the materials will be shared. Actually, I have shared the past 2 days materials to the corresponding coordinators. You will be getting the today's materials also for you. But I request you to go through that and then practice it. Only then you will get a clear idea like what is happening inside the design. Okay, I'll stop sharing. If there are any questions, please let me know. Yeah. So are there any questions? Please let me know. Over to Archana. Yeah.
No questions, sir. Thank you for the informative session, sir.
Yeah. Thank you. Thank you. Yeah.
Okay, sir. Now I would like to deliver vote of thanks. Now it's time to express our gratitude. On behalf of Electronics and Communication Engineering, St. Joseph's Institute of Technology, St. Joseph's Groups of Institutions, I would like to thank Mr. Batmanabhan sir for the informative speech. Thank you, sir, for taking out time from your busy schedule and joining us to share your knowledge. My heartfelt thanks to our beloved chairman, Dr. V. Baba Manoharan sir, for organizing a wonderful workshop to gain knowledge. My sincere thanks to our Managing Director, Mrs. S. Jessipriya ma'am, and our Executive Director, Mr. B. Sasishekar sir, for their guidance in conduction of the workshop. And I would like to express my gratitude to our Principal, Dr. P. Ravichandran sir, for his support to conduct this 3 days workshop, and our department heads, Dr. C. Nyanakausalya ma'am and Dr. G. Rohini ma'am, for their words of encouragement and guidance, and our department staff and organizing team for arranging this workshop successfully. And finally, my sincere thanks to all the participants for your active participation and support. Thank you all. And dear participants, kindly fill the feedback form. So the knowledge you showered through this 3 days workshop is unbelievable, sir. Being a final year student, I get to know lots of stuffs behind and for about field programmable gate arrays. Thank you for your step-by-step explanations and uninterrupted teaching for 4 hours, sir. Thank you once again.
Thank you very much. Yeah, it's my pleasure. Good luck, all the best, and then please keep in touch if you require any information. I'm definitely there to help you out.
Thank you, sir. Thank you so much.
Thank you, everyone. Archana, I will sign off, and then we'll meet later. Thank you very much. Yeah.
Thank you so much, sir.
Okay, sir. Thank you so much.
Thank you. Yeah. Thank you. Bye.
Thank you so much.
I request all the participants to stay connected. I will post the feedback form now, so kindly register on it.
அப்படியே சுட்டு சுட்டு வைங்க உள்ளார